So hello everyone, welcome back. So let's go for this final lecture of the in-presence event of TrustEat. Today we have with us Ioannis Athanasiadis, sorry if I said it wrong, from Wageningen University and Research, and he will be speaking about machine learning and digital twins. So thank you, Ioannis, for being here with us, and the floor is yours.
Thank you very much for the invitation. I'm really happy to be with you today. Let me again share my screen and see if it still works.
Okay.
And I will say a few things. Okay, how I do that now? We go to here, here, here. Yep. Can you see it now? Yep, perfect. Okay, well, good afternoon. My name is Ioannis Athanasiadis. I'm a professor of data science and artificial intelligence with Wageningen University. And I'm excited to be with you today. I will give you an overview of how we use artificial intelligence and machine learning for digital twins in agriculture. A little bit about myself. I have a background in electrical and computer engineering, and my passion is to do research on the interface between artificial intelligence and agri-environmental systems and see how we can use new data-driven methods for understanding nature and feeding the world. I think you all would agree with me that digitalization in agriculture is everywhere, from gene to fork. It promises to advance yields, to reduce waste, to lower supply chain costs, to contribute in matching all different kind of sustainability development goals. However, the key question is how. We have all components at hand. We do have experience with computational infrastructures. We do have big data collected gradually. We do know a lot about agricultural systems. And yes, data holds huge potential for the future of your farm, but only if you can figure out how to turn data into a decision. So how to do that? And let's first start from where we stand today. As I said, we have all components in hand. We do have databases, model bases, model catalogs for data storage. We do have a lot of experience with end user applications, decision support systems, and gradually, I think in the past 5 years, also with modeling and so on. The key question there is how big data ready are all these technologies, and this is what we will discuss a little bit. So what we miss, in my opinion, is twofold. One has to do with exchanging data in a meaningful way. So whenever I start a collaboration, the discussion always goes like this. I need this kind of data, and well, here it is my data, but not exactly the same. I can produce air temperature maximum, but who can calculate it on a daily level, and so on. So it's very difficult to actually meet the needs of data that are required for modeling, whatever kind of modeling, including machine learning, with what data is available. So this kind of agreement is very difficult, and most of us are typically lost into this kind of discussion. So it more looks like a bubble, and this is a figure of a project that I was working about 20 years, 15 years ago. And a lot of things have changed, but let's see what and into what direction. So in a way, what happens is that there is a mismatch between data infrastructures, and data analytics. And this is because agri-food systems involve uncertainties of cross-scale phenomena, inherit the difficulties of massively collecting data, heterogeneity, noise, natural variation. So it's common ground that despite the increasing volume and variety of sources of data becoming available, data are not necessarily useful for improving our understanding, for farmer decision basing, for policy choices, for company recommendations. And there are several reasons for that. At the same time, our models, either theory-driven or simulation-driven, have reached their limits, as they often exclude several factors at different scales. It's hard to reuse them, and research is fragmented in non-comparable case studies. In that sense, it's very hard to extract value out of data. There is a gap between data infrastructures and data analytics. And the way forward is, in my opinion, not only to close this gap, but do this in an iterative way so that we are collectively or continuously, both collectively and continuously, improve data infrastructure, work with data analytics, and do this cycle again and again and again so that we can extract value out of data. But also, at the same time, we need ways of instilling our existing knowledge into this process. And I will explain what I mean with that. And in the past, let's say 20, 25 years, for example, I will give you a couple of successes of data-driven discoveries in agriculture that probably you are aware of them. There has been a huge number of scientific studies over the past 25 years that have shown that measurements in visible, near infrared, thermal, microwave wavelengths of light can indicate when crops are under stress. And we are using extensively image-based remote sensing for detecting vegetation density, water deficit, or crop stress. And these have started about 25 years ago with initiatives from the US and NASA. And now it has been turned into products of several companies and farmers, and bringing this into actual use. Another example, a little bit more academic, is what happened with plant phenotyping, where about 10 years ago, a couple of people started annotating images and turned the whole plant phenotyping, leaf counting, leaf detection problem into a machine vision problem. With time, the performance of this detection has increased by a lot, going from 74 to more than 90%, or the detection error from 2.6 down to 0.7. And now it's a mainstream technology used in digital phenotyping infrastructure. So how does the farm of the future or tomorrow looks like? Will there be, and we have this very nice cartoon on some of the Wageningen initiatives, and I think it's very interesting because it shows exactly what we have. I have been talking about. So we do have all components ahead. We have weeding machines, optimal breeding with AI and robotics, pixel level farming, circularity, hands-free farming. All these are new concepts that are supported and enabled by data science and AI. But in order to do that, we need to crack the data landscape. And what happens in practice is that in order to enable these data-driven discoveries in agriculture, we need to bring together data at different scales, from landscape level and remote sensing data down to genotypes and genotypic information and whatever comes in between, including climate, economic, agricultural machinery, farmers' blogs, crop calendars, historical yields, cultivars, and so on. So the way ahead, in my opinion, and this is what I'm going to be talking for the next 10-15 minutes, is what is the way ahead. So the way ahead, in my opinion, is that there is an era that is in shaping now where new data-driven, data-intensive scientific discoveries will be enabled through artificial intelligence and digital twins that are able to learn across these heterogeneous data at different spatial and temporal scales, but also needs to be able to encode prior knowledge into reusable models and make trustworthy, useful estimates in new conditions. And digital twins is an essential component into this. It's a concept that have started being using about 40 years ago in more industrial environments, but practically the concept is that for every situation we have a dynamic virtual representation of a physical object or a system that uses real-world data, simulation, or machine learning combined with data analytics in order to enable understanding, learning, and reasoning. So, and the deal there is that is kind of new, is that digital twins then can be used to answer what-if questions and should be able to present insights of how to deal with new situations without having to actually implement them in practice. And key distinguishing features of digital twins is, on the one hand, to have real-time sensing of data in one way, but also to be able to have a model for every individual, for every particular case. So not to have a generic model for a region, or for a farm, but go into individual farms, individual pixels, individual animals. But also a key component is that they should be able to learn. As that means that as time passes, we need to, these digital twins are able to adapt, learn for the particular individual with a particular local conditions, how to make better decisions. So a key attribute, in my opinion, about digital twins is not necessarily the real-time or user interaction or decision support, but their ability to learn for every individual plant, animal, location in a company or branch or whatever, based on your application, how to improve decision-making as time passes. And to do that, we need to bring together data from different domains like genetics, management, and environment into smart data observatories that then in turn will be analyzed with data-driven hybrid AI, and I will give you some examples of both of those, in order to create these digital twins that is able to monitor the world, learn, and give advice and help us improve decision-making in silico, without having to try out in practice different scenarios. So we had, before we go into some actual work that we have been doing towards this direction, I think it would be relevant for our discussion today to share with you some of the results of a recent review paper that introduced digital twins to agriculture. And long story short, still most digital twins in agriculture remain in an early concept stage, especially those operating in open fields, in farms, or at landscape levels. And on the other hand, in terms of functionality, most digital twins aim for real-time monitoring or system failure analysis and control, and less into other kinds of operations like technology integration or virtual maintenance or other kinds of operations that we see in other domains. The results of this review also strengthen our belief that digital twins in agriculture make currently their first steps, and a hybrid approach is necessary to reveal their potential. And let me explain what we mean by this hybrid AI approach. As I said in my previous slide, this hybrid AI needs smart data infrastructures, and for that we can use artificial intelligence and semantic web technologies for reusing agri-environmental data. And here we see some of the results of a PhD student of mine who graduated a couple of years ago, where we managed to use logical reasoning to bridge the gap of different definitions and have even smart devices like this Raspberry Pi that was able to monitor environmental conditions, but also publish them on the web using open standards that then can be mediated with different standards and enable us to really use artificial intelligence not only to learn from data, but also to share them. And in a similar direction with the work we did with Papazoglu, also in Wageningen, we use semantics for enabling the reuse of genotypic and phenotypic data, and we co-developed the MyAPI standard, which is now universally used by plant breeders for sharing information. So that's the first pillar of the work, that we need to use AI components for sharing data and for building smart data infrastructure that is able to mediate automatically, have machines that automatically mediate between different data sources. And the second component is to use machine learning and data-driven methods for learning from data. And I will show you a couple of case studies of works we have done in the past. So this is an ongoing work that we're doing with Dilip Paudel, a PhD student of mine, together with the Joint Research Center. And here we use machine learning for large-scale crop yield forecasting. So what's the Joint Research Center of the European Commission has is a system already in place that uses weather monitoring, crop simulation, yield statistics, and remote sensing for having yield forecasts. And based on these yield forecasts, they have some software tools for generating maps and stuff, but also they publish a bulletin to advise policy makers, but also other kinds of industries about what will be the yields of the current season. And they do that all across Europe. They issue new bulletins, I think, every month from March till September, October, something like that. So our challenge, and also what they do is that their forecasts are done at the national level, and this is because they involve also a lot of human expertise in building these models and suggesting this kind of yield forecast. So they have also, and to do that, these experts take also under account other types of informations like magazines or other sources and so on. Our challenge there was to see if we can, by using machine learning and artificial intelligence, improve yield forecasting all across Europe for different crops and for different countries, but also to if we can downscale it down to regional and sub-regional level instead of having forecasts at the national level. And to do that, we built a reusable machine learning pipeline system that works across scales, crops, and regions, is inclusive and explainable. And by this, we mean that we have included crop modelers and scientists from the Joint Research Center in the design of the system, in the selection of the data sources, and so on. And we devised an agronomy-driven feature engineering process on what is selected and why and how we organize our data. So a lot of expertise from the domain was involved in this. And then we tested this in 35 case studies in 9 countries and 6 crops. And with our system, we improved the predictions at the national level for early season in 25 out of 35 case studies. That's the best, without being very, I will try to say it in a modest way. This type of yield forecasting at the regional level in Europe haven't been improved for more than 10 years in terms of lowering errors and improving predictions. So that's a very big step forward for them. And another thing is that we were able, as you can see in this map, to give predictions at the regional level, not at the national level, because this solution is scalable, so we can scale it into a regional level, and this already can give policymakers and insurance companies and different stakeholders in agriculture not only what is the general trend or expectation at the country level, and here in the big countries like France and Spain, you can also see visually where in which regions or sub-regions we will have higher or lower yields or whatever. Another thing that is also very important is that while we improved predictions, we also managed to reduce the error and the uncertainty of these predictions. So even when we are not performing well, as you can see in these box plot diagrams very quickly, we managed to reduce the uncertainty and compared to the operational yield forecasting system that includes also additional information streams that were not available to machine learning, reduce the uncertainty of prediction, so increase the confidence of our advice. And this is an example how machine learning can be used in order to both improve predictions, but also start changing the support we can do and the digital twins we can do, that by going more specific into from a national level down to subnational, regional, sub-regional, and in a higher resolution. And that's a case study of ongoing work that we do. Another one that I will bring on the table for discussion is a case study where we use digital twins for tactical pasture fertilization decisions. So here, the problem was to build an operational decision-making or decision support system that is able to give advice to the farmers when should they fertilize grassland pastures and with how much and what is the return on investment. So what is the additional yield they get for every kilogram of nitrogen they apply? And that's an important thing that we considered by involving domain expertise and domain knowledge into this solution was twofold. One had to do with what is the minimal information that is easily available on every farm. But the other thing was also to transform the prediction problem. So instead of predicting yields, we were predicting the nitrogen response rate. So what is the relative gain per kilogram of nitrogen applied? So in a way, instead of looking into absolute figures, we're looking at the business value figures that are relevant for the decision makers in this case. And what we did here was to build on an extensive synthetic data set that learns from 1.3 million simulations. So in 8 locations in New Zealand, we run 1.3 million simulations with a crop growth model called APSIM, and we generated a really massive data set that covers all different environmental and management combinations. So we created a massive synthetic data set, and we learned from it. And again, here, the results were very impressive. So here in these box plots diagrams, you see the errors, the residuals for the 8 locations on the test set. And what is really important for this is that when we started discussing with our stakeholders and end users of such a system, we have been discussing what would be an ideal threshold. So, of course, there will be some error in these predictions, but what would be an ideal threshold so that such a system could actually be used in practice? What would be the actual level that farmers might start considering actually using it? And their response was that, well, typically errors in such systems are about 10 kilograms of dry matter per kilogram of nitrogen. So if you could make it around 5, then we are in a very good situation. And yeah, these numbers are a little bit small, but 5 is somewhere here. So in most cases, also here, in the huge majority of cases, our errors are really operational. They are allowing us to build. They allow us to have a machine learning model that is tactical, that can really give tactical advice to farmers using really minimum information, only 4 weeks of weather and prior to any fertilization. So we don't use any future weather forecasting, only by looking at what happened in the past month before the day you want to make a decision. We could give the farmer an advice what would be the return on the investment he makes in applying fertilization. And that's very important for reducing the use of chemicals on fields, but also I think it contributes to this other point I made also in the beginning, that it's very important to integrate and consider the actual knowledge of the domain and the needs of the end users. Last but not least, a third way, or another case study that we use for machine learning for building digital twins in agriculture is a case where we are using reinforcement learning for optimizing nitrogen fertilization strategies. And here we have machine learning to learn not to make predictions of nitrogen level applications or crop yields, but actually learns a policy that is optimal by interacting with in a virtual environment. So what we have is the goal of machine learning is to train an agent that is observing a virtual crop, in our case using the WOFOS simulation environments. And the agent in silico is able to apply different actions like fertilizing or watering plants or whatever. And based on its actions, it gets a reward. And in this case, we were rewarding the agent for the weight of the storage organ, so for the more yield he manages to produce in this virtual field, but also we were penalizing the agent for the more fertilizer it was applying. And what we wanted to do is to let the agent learn by trial and error, by reward, what would be an optimal strategy for fertilizing nitrogen. And here we see some results on the right. We compared this agent, the reinforcement learning agent, which appears with the red in the third bar. We compared its performance compared to the standard practice of the farmers, so what they do, and also with a dummy agent, a reactive agent that whenever looks at the soil profile to have a nitrogen deficit would apply some more. And on top we see the weight of the storage organ. So what is the yield that the agent manages to produce? And in the bottom one, we see the amount of fertilizer it applied. And of course, the reactive agent was doing very stupid things and was applying really huge amounts of nitrogen. But if we compare what this intelligent, maybe, agent is able to do, we can see that it was able to produce more or less the same yields, while in most of the cases, it was using the same or less nitrogen. So in this way, we could, and this is an example of how we can use machine learning for learning how to give advice to farmers for reducing the use of chemicals, nitrogen, without reducing a lot their yields, without having to learn from data, but learning from in a simulated environment where they can, the agents play around, they're allowed to fail, they're exploring a huge combination of different situations without having to actually implement those in practice to see what is their actual results in reality. And this is where the this digital twinning concept comes again into the game. We are able, with this kind of methods, to in silico evaluate scenarios and optimize policies, learn policies without having to actually implement them in practice. So, okay, you can say these are very interesting, and well, I would be happy to answer some questions if you have later, but also I would like to bring your attention a little bit on the issue of the promise of all these technologies. So machine learning has been, brings new opportunities and solutions, but also at the same moment, they are not yet out of the box, ready to be applied, and depend very much on the domain. The transition from generic AI machine learning applications to agriculture specific is emerging. So, and the digital phenotyping one is a result, but also this is the experience we had with my group in developing these applications that it's not always very straightforward how to apply and where. And there are a lot of new knowledge and development that needs to happen for all these methods to work. And this is some work we did with by going into stakeholders and had a survey for a European project that we were involved. And the key question here was, what is the key driver in all these big data applications in agriculture? So what is the most important factor and what is the least important factor? And we asked them about 4 kind of aspects. Is it data interest? Is it a technology interest? Is it research interest or a commercial interest that drives this development? So, when I say data interest or data opportunity, is that there are so many data available, we don't use them then, so we need to do something with them. Or there are new techniques or technologies that are available that we don't use yet, and because of that, we want to invest and develop further machine learning, data-driven, big data applications in agriculture. And then, as you see, the view of the stakeholders is kind of spread out in all these 4 drivers. But when we ask them, so this is what drives their interest in big data. So it could be the availability of data, the availability of technologies, their curiosity or needs to answer, to discover new solutions, or in other case, an opportunity to gain competitive advantage. But when we ask them what is hindering the adoption of a solution in their industries, cost is the most important factor of stakeholders. They're also concerned whether this solution can be embedded in what they currently have, or how the personnel can actually work with it, and so on. But practically, the key issue is the availability of financing or the high cost of this. And also the free entries that we can see here also brought some interesting reasons, like the lack of return on investment estimation, or the small lands or land ownership or farm sizes in Europe. To bring it all together, I have, I think I gave you an overview of how artificial intelligence and machine learning is changing digital agriculture. And the future, in my opinion, is towards an integrative artificial intelligence where novel data-intensive discoveries will be enabled by new collaborations that go beyond disciplinary boundaries. That's a key message that I consistently bring up, because it's not that by analyzing data only we will find a lot of things. We need to include and direct all these machine learning systems with things that we already know, so that we find new things that we don't know from data. Also, a second point is that such artificial intelligence needs to be transparent and explainable and well-founded on existing food systems knowledge. We don't need to have these data-driven systems to tell us things that we already know. But also, it's important to direct all these investments and knowledge of new sensing technologies, data infrastructure, machine learning and artificial intelligence to address the right problems, to address long-standing challenges, not only for toy examples, not only for things that could be useful, but the key challenge for me is to actually see how we can solve problems which are useful. So to have a real impact in our domains and go from talking about the potential into the actual. And with this, I would like to thank you very much and maybe open the floor for questions and discussion. Thank you very much.
Thank you very much, Ioannis. So any questions? Yeah, Marta.
Hello, Ioannis. Thank you very much. It was really very interesting. I have a question related with this evaluation that you performed with the stakeholders. How they were willing, no, to use these systems, no, and so on. Mm-hmm. Did you guys evaluate how was the differences between different areas in Europe? Because, for example, in the case of of what you were mentioning about the nitrogen, use and so on, I know that, for example, in Netherlands, this is a big issue, so there will be much more concern, right?
Yeah.
I wonder how are the difference between the different areas, or if you have the chance to evaluate.
Okay, very good question, because actually that's something we didn't ask them for. Huh? So we didn't ask them about what their concerns, because obviously you're right. In different areas or in different locations and in different industries, we have different priorities. So yes, we are very much influenced by being in the Netherlands. So it was about nitrogen, but if we were doing that in Greece or in Spain, it would have been about irrigation, right? And the same principle of learning from a simulated environment is something that does work and works very well. And actually, to give you another example, we have recently published a paper together with ETH Zurich, where we are using a different simulator that is able to simulate across several years, and we have been training agents that manage both irrigation and fertilization and multi-year effects. So not only what is optimal for doing in a season, but also getting into account soil health and long-term effects for improving yield. So I'm not saying this is still, that's maybe a little bit of the frontiers of the state of the art. I'm not saying that this is necessarily ready to be used in a farm, but I think the potential, and that is the challenge. How can we go from talking about the potential that we researchers do into the actual, that actual companies, SMEs, startups want to achieve? And there is, I think, a gap that we need to fill it in, both in developments of methods, but also in defining the right problems and sharing the data, the right data and the right environments. Because, and I think I'm getting a little bit further away from your question, but a key challenge in our domains is that it is very, very little standardization of problems. So in a way, every farm appears to be absolutely different than any other, because it will have different equipment, it will have different composition of activities, all these kind of things. But essentially, we're talking about the same things. So the point is, if this, there is an underlying model of how plants grow and how animals are growing and produce meat and milk and so on, and how nature is able to cope with all these activities we do on top of it. So, and I think that's part of the main challenge for the next years, how we can really make these things work, not in a particular experimental farm in a university or in a prototype condition of a big multinational giant, but to make it available and useful for all. Either they are small SMEs or farmers or different types of companies in the sector.
Yeah, I fully agree. Thank you very much. It was really, really great.
Thank you too.
More questions? Nope. It seems there are
Should
no.
I ask you a couple of questions then? What do you think?
Yes.
So I don't know a lot about you, but according to your opinion, to what extent do you think that all this AI, machine learning is a little bit of a hype and it will go away?
Do you want to reply?
I mean, if I were there, I would ask you maybe in a different way, but call it a hype. Like we could also, and you're recording me, so I cannot be very straightforward about it, but I think you understand what I mean.
This is Marta Prado again. In my opinion, of course, it's a hype, of course, like many other things, but I really see the potential. I really see that it will be, with these cases you were mentioning about the soil health, the irrigation, these are problems that we have in different areas, and we will need new high-tech developments to be able to produce all the food that we will need in the next years, because so I think this could be one of the technologies that have that will have a really an impact, in my opinion. But maybe I'm.
Yeah. Shall I ask you to give the microphone to somebody else?
Yes.
I mean, I don't want to point any
I'm
fingers.
trying to push them to say something else. Maybe Hugo.
Yeah.
Okay. Yeah. First, thank you for the presentation. Pretty interesting. My name is Oliveira. I'm a staff researcher here at INL. I have a kind of more a question than a comment.
Oh, sure.
It's a little bit about the sources of information, and so of course we know that all this, let's say, data that is, or information that is acquired through different levels, from satellite imaging through weather stations, and of course all the data sets and historical records. And what is your opinion also about the chemical information? Yeah, I'm a little bit interested on that because I work mostly with try to generate chemical information. So what is still in the level of the incorporation of chemical information acquired in the farm about soils and even the plants, and yeah, what is your opinion on that based on your experience?
You mean what is available, or
yeah?
What could
so
be available?
what is under use currently for doing this, applying this kind of techniques, and what kind of information do you find could be useful also to incorporate in the future, based especially chemical information? I know that more information is of course in principle useful, but yeah, what is your opinion on that?
Yeah, I mean, that depends on what you mean by chemical. So, for example, pesticides is much easier to record because you use an appliance to spray them. So you could automate this kind of processes and start tracking them. And in some of our projects here, we actually have robots or smart devices that actually can micro spray at the pixel level and even at the plant level for pesticides or fertilizers and so on. When you talk about soil health and stuff, there maybe I'm not the most qualified to speak about this, but I wouldn't think that within a field there is so much big variability in terms of soil health, or that the changes in soil health is something that you need a continuous monitoring. But I'm not qualified for that, so really take it with a grain of salt. That's from what I have been seeing from my data science adventures, not as a soil health scientist. At the same time, I do know that there is a lot of efforts for building low-cost sensors for detecting soil moisture, soil fertility in situ, but also to have these kind of things measured with satellites or inferred from remote sensing images, either from satellites or from drones. So there is a lot of development also in the sensing equipment or potential, which also brings a lot of interesting new data streams that were very expensive to do in the past. So typically in the past, about soil health or soil conditions, a farmer would get a sample and send it to a chemical lab and have maybe one measurement every few years, in the best case, or maybe once, and then this is it, so keep on going. Well, I think very soon we will start to be able to have better measurement process for this kind of processes as well. Yeah.
Okay, thank you very much. Any other question?
May I comment a bit about the hype towards artificial intelligence or not? So I think that sometimes we should, especially the one of us that are more involved into data modeling, should be actually ambassadors in trying to remove this hype and go to the substance. So what I see as a referee, as an editor, as a journal editor, is that like 90% of the cases, especially in the domain, in the domain of food chemistry or agricultural related problems, like artificial intelligence is abused. So it's used in situations where probably a simpler model would have made better and would provide more robust and more interpretable results. So I think that at least the one of us that are more cautious about that should do an effort in trying to demystify what is behind artificial intelligence and try to push towards a rational use for the cases where the advantages of such approaches is actually relevant and not about the abuse of that.
Yeah. And the truth is that it has the, I agree with you. But I think part of this has to do with the speed that AI developed in the past 10 years. So from being something marginal for a few geeks and so on, it became something which is mainstream and is actually everywhere now. So you want to interact with your bank or whatever, you have an AI chatbot that talks to you. There are no humans there. Or you can get all these kind of fake images of Van Gogh that can shows, I don't know, things that didn't exist when he was there. You can get all these kind of deep fakes and stuff. So we can, but also very useful things like all the machine translation things. I speak no Dutch, but whatever comes to my email in Dutch, I put it on Google Translate or similar platform from Bing, and all of them work perfectly well. So in that sense, there are also a lot of things that change really fast, and all this happens maybe in maximum 10 years. So that's really fast for technologies that to go not just in application, but actually change the life of people and being omnipresent. I don't think you can be anywhere anymore that there is no artificial intelligence around you doing something, which is kind of shocking. It took us decades to do the same with telephone. So just to give you an example of another technology. So in a way, it also comes very fast, and that's why I think that a lot of people are a little bit cautious as well.
Any other comments, questions? No? Okay. Any other questions, comments from your side, Ioannis?
No, I think given the time, maybe it's best to say thank you, and thank you for joining. I hope you enjoyed the lecture. And if you have any other suggestions or ideas or comments, don't hesitate to contact me, of course.
Okay.
Yeah.
Thank you very much.
Thank you too. Thank you for the kind invitation and the nice hour we spent together.
Thank you. Okay, so now it's over for the in-person part of the TrustEat Summer School. Right now we have the bus that should be waiting for us outside for those that want to go to the winery cellar. And tomorrow we will have 2 online sessions that will be about use cases in the food and the agri-food sector, about open source blockchain in the food sector. And yeah, it will be online, so you don't need to come here. You just need to go to the link that we sent, I think, today to you. And that's it. I really want to thank you for being here all these days, and hope that you have learned something, and hope to see you soon in next activities. Thank you.
So, yeah, welcome back. And can you hear me well and everything? Okay. So, I will present the presentation just before lunch. I have 1 hour, but I hope I will be shorter. I will try to, okay? But please feel free to ask me questions, or, catch me after it, and we can talk about it, okay? The presentation is Advanced Miniaturized Devices and is used with blockchains and distributed ledger technologies. So just a brief introduction about myself. My name is Marta Prado. I'm the research group leader of the Food Safety and Quality Research Group. You can get more information about ourselves either in the QR code or in the webpage directly. We are a group that is, we move a bit in the number of people that we have, but we normally have roughly around 10 people between PhD students, staff researchers, and postdocs, etc. Okay, and we have also roughly around 6 different nationalities in the group. We are working in the TrustEat project. We are one of the research group involved. And if you if you have been present here in the previous days, you must notice that we use this schema a lot because we are working in the different layers here, and our work is mainly on the physical layer. Okay, so we work in the sensors, smart sensors or advanced sensors, as you will see later. Okay, although we kind of touch a bit the part of the application, as you will see later on, right? So the presentation will be divided into these 4 main points. I will introduce the motivation, why we are doing what we are doing, what is the final aim, let's say, the objective. What are we trying to do? So from the problem that we have, what do we want to do? How do we want to solve this? And the third point will be that how are we doing this? How do we do that? I mean, what is the approach that we have to get to solve this specific problem, let's say? And then I will introduce what is next, what is the next project that we have somehow related with blockchain technology, and as well related with this, a bit with this project as well. So regarding the motivation, food fraud, as you can read here in this definition from the European Commission, is any suspected intentional action by businesses or individuals for the purpose of deceiving the purchasers and gaining advantage, mainly economic advantage. And there is like 4 main factors that you can see here to consider something as a food fraud. One is the violation of the EU rules, so you are not following the rules for labeling, for example, of one specific food product, you try to deceive, you try to trick the consumers, okay? And this has, of course, implications because a part of your own, food industry, this specific food industry, it affects the trust of the consumers in the different food products. Then it has to be associated with an economical gain, and it has to be intentional. We will see later that there are, different kinds of adulteration. All of them are intentional. In order to be considered as food fraud, it has to be intentional. So, regarding food fraud, there is also different types, as you can imagine and you can envision here. So it could be a dilution. So you are missing an ingredient with a higher value with something that has a lower value. So yeah, this is considered a dilution of the product. And maybe these ingredients are all of them in the labeling, but the one that is considered with the higher value is in a lower percentage than it was supposed to be. Okay, a substitution, so you just change one product by another. The concealment is when you are trying to hide some low quality ingredients or something that is not in the perfect state, let's say. And so on and so forth. So there are others like unproven enhancement, then counterfeiting. So you are indicating that your product is, for example, from a specific denomination of origin that is not. Mislabeling, that you are indicating as well is related somehow, that is related with, putting something on the label that is actually not true. No? And this is happening, more often than we might think. And we can see here some very famous cases. So those of you that are, from Spain might remember this rapeseed oil event, that it was a very, very big issue, and it has a lot of implication. Many people died, and a lot of people had problems, health problems, for many decades. Okay, and there was a big trial in Spain and so on. Then there was the case of the melanin in baby milk, okay, that you might remember as well. That it was as well a big issue in the food industry. Yeah, methanol on illegal spirits, and the horse meat in beef roast. There are many more, but these are, some of the food fraud cases that kind of were in the media for the worst reasons, let's say. So, just to give you a small hint about what happened with the horse meat scandal, and for you to understand how big that was, actually, because, well, we might think there is not a safety issue with substituting beef by horse meat. But, of course, horse is not eaten in any countries in the same way. The consumer has the right to choose if he wants or she wants to eat whatever the product it is. And if we are not indicating this in the label, well, we are affecting the trust of the consumers, okay? This affected 6 different countries and 11 companies, okay? And there was a huge sales drop. And in principle, there were not health implications because, well, why substituting one animal meat from other animal meat normally is not an issue, apart of deceiving the consumers. But in that case, some of this horse meat was coming from horses that were from, like, race horses, okay? So the sanitary control of these animals were not as strict and those that were intended for food production, okay? So some of them were, horses, race horses that had some health problems, so they were having some drugs, and so these drugs could be found on the meat as well. So that was a bigger issue that we might think of. Then, regarding all these issues that could affect the food products, Whether they are intentional or not, we can divide it onto a food quality issue, food safety issue, food fraud, when, as I mentioned before, when it's economically driven. Then there is another case when it's ideologically driven, so cases that somebody, just to harm a company, just to harm a specific group of population, for example, adulterate something. That's a case of food defense, okay? And then the typical, related with food safety, when there is an accidental contamination with some foodborne pathogen, or there is some, for example, allergen that is not indicated, but it was not a substitution, not intentionally appearing there, it was a problem of cross-contamination, for example, that will be a food safety issue. So, more specifically, related with what we are working, or what I'm presenting here today, olive oil is a very highly valued product by consumers because it's associated with some health properties, because it has a good flavor and taste, and it has also a high price compared with other food products. Okay. It has been identified as one of the products with a higher risk of being adulterated fraudulently. Sometimes the olive oil is diluted or substituted with other oils, okay, such as sunflower or other cheaper seed oil. Sometimes the adulteration is related with the production system, so sometimes it's labeled as extra virgin olive oil and it's not, etc. No? Another issue is that more and more there is a high interest from consumers on buying local products and also from producers to put into value local products. Okay, and this is an important trend, and it's an important step to contribute to the growth of local communities that are producing these products for a long time and so on. And there is also an interest on recovering some autochthonous varieties, to put into value these autochthonous varieties that are coming from some specific regions. And the consumer is also quite interested at the moment on buying local, on buying sustainable, on buying something that is authentic or they identify as authentic. But it's quite difficult to prove this, okay? So that leads me to the next step, that is the second step, what we are trying to do, after all this introduction, what is the point, what do we want to do? So we are focusing on detecting fraudulent practices on olive oil. Traditional analytical methods are normally not adequate or sensitive enough or specific enough for the detection of certain of these fraudulent practices, okay? Although, of course, we can combine, for example, with data fusion to have different type of analysis with different equipment and so on, and try to solve some of these problems, but for some specific issues is quite difficult. And the identification of olive varieties is particularly difficult, okay? It's already difficult to make this differentiation between different seed oils, although there are methods there. But olive varieties are quite difficult to differentiate in a sample. And another point is that it's quite important to make this technology accessible for the producers, from the different stakeholders on the food value chain, in order that they can self-monitor themselves, they can know which type of raw materials they are buying, they can make sure what they have in their farms, because sometimes it's not so straightforward as we might think. There are varieties, for example, that are very, very similar. And until they grow for a long time, they are not 100% sure sometimes that that they are the variety they were waiting for. You know, it's even difficult for the most experienced ones. Oh, I don't know what happened. Okay. Yeah. Okay. So this is an example. Sorry, this is an example of the olive oil value chain. So as you can see, there are several steps. They can happen in the same producer, or they can happen in different producers, actually. So, you know, there are, for example, cooperative associations that they gather together olives from different areas, or they do the first step of the production and then they send it somewhere else, etc. Okay. So, can we control, can we control each of these steps on the production, on the food value chain? How can we do that? How can we do that in a simpler and easy way? So, and this is what we are trying to do in general in the group. So we are trying to go from the lab to the field, so developing miniaturized devices that allow us to do complicated analysis on site, on the field, or on places where there are not enough equipment to perform this analysis. Is what we call as well decentralized setting analysis, so bringing the lab to the different points. But despite there is a lot of advances on miniaturization of analysis, there are certain analyses that are still not there. You know, for example, we saw the example with the citrus sensor that is super cool, by the way, from Gianmarco that he presented yesterday, and this is very nice device, and we saw as well the one that Hugo and Joao presented yesterday with the eye grape and so on. But sometimes the type of analysis are slightly more complicated than that, although those have as well this complication, and the data analysis as well quite challenging. But thanks to the miniaturization on the development of micro and nano fabrication, we are able to develop advanced sensing in these miniaturized devices, okay? And the idea is that we can contribute to a better control on the food value chain. And how do we do this? Well, here, two of my former PhD students setting together a DNA model. We are working mainly in the group with DNA because it has a number of advantages. It allows us to have a very high specificity. So, you know, from many previous cases, no, that DNA allows us to identify very well individuals, species, etc. No? And it allows us as well to identify varieties, which is something that is really interesting for us. DNA is also a double-stranded molecule, and we can play with this reverse hybridization, allowing us to detect very specifically a complementary sequence of what we have identified. Another advantage is that it's not affected by the variability of the phenotype. This is important, for example. If we talk particularly about plants, sometimes the protein content is affected by the season, by the weather, by many other points. And in the case of DNA, we have the same DNA content in the different cells of a specific organism. So that's another beneficial factor of using DNA. Then it has a high stability, so we can detect DNA from mummified tissues, bones, forensic samples. You know, it's not as easy as they do in the movies that they just take a small sample and put it in a, and they know who was the killer. But yeah, it's possible to do that. And what is most important for us is that you can detect DNA. It's still stable in processed products. So some food product that has been subjected to high heat treatment, for example, or it was involved in a fermentation process, etc., well, it has relatively high stability. And then another important point is that it allows us to have a high sensitivity because we can amplify enzymatically a specific DNA sequence. You know, I used to talk a lot. I mean, I used to explain what PCR was, but after COVID and so on, everybody knows already what PCR is, no? So just we can kind of photocopy a specific DNA sequence in order to be able to detect it, even if it's in a very low content, okay? And then another point that is quite important for us is that it's relatively easy to functionalize nanoparticle surfaces with DNA molecules, okay? So in this specific case, we had to think how we could put something, a method that is really complicated into a miniaturized device. So the first thing that we did in the frame of this NanoEaters project was to evaluate the different DNA markers for variety identification. Okay, so we make a review of all what it was in the literature to really identify these different varieties of olives, and evaluate, okay, this is something that allow us really to differentiate very close related varieties or not. And this might seem easier than it is, but it's not. And as another point that we had in mind is to that a part of the target that we will use, that we will be able to develop a method that we can put in a miniaturized device. No? Not all of them. I mean, we could use DNA sequences, you might think, but this is when we want to do a non-targeted analysis, but we wanted to do a targeted analysis in our case. And many of the techniques that are used to identify varieties, they require a quite sophisticated equipment, such as capillary electrophoresis or other techniques, okay? So we wanted to have something that will allow us to identify very well a specific variety, and at the same time, simple enough to put it in a miniaturized device. So we evaluate several techniques for the identification of the simple sequence repeat. That is a DNA sequence that it was identified before in the previous study, that one interesting one for the differentiation between olive varieties. And we use it to differentiate with different techniques, all of them using DNA, olive varieties from the northwest of Spain. So we have, there were two specific varieties, like very old varieties, very autochthonous from this region that are nowhere else, and we wanted to make sure that we could differentiate them from others. So we developed a method that is called real-time allele-specific PCR. If you are interested about the details, you can go to the paper itself. And then we also developed a miniaturized cartridge to perform this technique. So we use microfluidics, okay, and we needed to have this suitable method that could be integrated in this cartridge, so we could bring it. And we fabricated a miniaturized device that allows us to control the temperature during the amplification, and also equipped with a detection unit that was an optical sensor that will allow us to detect possible change of color that will indicate, okay, the presence of this specific variety or not in a sample. Then another point that it was very, very challenging when we are thinking about miniaturization of analysis, it was the sample preparation, okay? Sometimes, we say very often in the group, we have to think how to put a hamburger in a chip, no? Okay, it's very nice to have a chip, very nice to have a fantastic sensor, but we have to think about the final application, okay? So Although DNA analysis is a very powerful approach and it has a high specificity, sometimes it's not used because it's very difficult to purify the DNA from a complex matrix such as olive oil. And it has a very low content of DNA in addition, okay? You can see there that, the matrix is very complex, the olive oil is a very complex sample, plus the DNA content is very low, so we have to make sure we have enough in order to analyze, no? In order to make it usable. So for the sample preparation, we combine microscale solid phase extraction and microfluidics. Microscale solid phase extraction is normally used in kits, in methods in the lab to purify DNA. It's a very powerful technique. What we do here is to bind the DNA specifically to a solid phase. Then we do a washing step where we eliminate everything that is not DNA from the sample passing through. And then we recover, we change some specific characteristics from the buffers, from the sample and so on, to recover the DNA that is on the solid phase to the liquid in order to be able to analyze this. And we combine this with microfluidics because we can develop these devices, integrate all these, the solid phase with the fluidic control, etc., in order to perform this DNA analysis. And then we develop a method. Here is one of the, our initial prototypes. It's a rather simple prototype, so we have a silicon membrane that is that we are using as a solid phase. We have a PMA-made top and bottom where it gives us the solid cartridge part in order to control the fluidics inside. Then we have also PDMS O-rings to make everything compact and to avoid that we have any liquids from it. And then we develop a method consisting of one initial and very simple pre-treatment step, because we needed to separate the oleus from the aqueous part, and then to take the aqueous part where the DNA is to the device, and we optimize this, sorry, second, back, yep. So the idea was that we could, purify it and extract enough DNA in order to be analyzed by the other technique that we have developed that I told you about before. So here you can see that we compare our device, the miniaturized device, in yellow, orange, and the commercial method in green. We use extra virgin olive oil directly, and also we spike some extra virgin olive oil to make sure that we were, taking into account what we were extracting, and we have a reference to it. And we demonstrate that the concentration of DNA obtained with the miniaturized prototype was higher than with the commercial kit, so we have a higher DNA yield from the samples, and it was 3 times higher for the spike extra virgin olive oil, and 6 times higher for the non-spike, for the natural sample, let's say. Okay. Also, you can, if you want to have more details, you can have here. Then the next step, we have this miniaturized device, rather simple device, that included the cartridge, where we had the sample preparation area and the DNA amplification area, plus the area where we could read the results. It's an optical detection, so there is a change of color. So with this change of color, we know if the specific variety is there or not. And this was integrated on a miniaturized device where we have the peltiers for the temperature control and a simple optical sensor. and all the flow control as well. And then we were lucky enough to, to collaborate with our colleagues from the Technology and Engineering group in the frame of an internal call at INL. And now also we keep collaborating in an Interreg project, in the EVA project, for further developing this device, and included very fancy things, by the way. Let's see if I can, that you can see here in the video, okay? So you will see that first, well, this is the integrated microdot analysis system is how we call all these steps integrated into one specific device. So this is the device, the design that they did. So they include the tubing where we will put the reagents. They also have you know, well, you will see this in more detail, but there is like a touch screen control, and then the temperature control. So there is some refrigerating system and heating up system. There is the area where we insert the cartridge, okay? There are two areas where we can read the cartridge, as you will see later. This is for the flow control. You can see in this microfluidic rotary selector. So all the tubing with all the reagents that will come into our cartridge will come from this, and we can control as well with the machine. And you can see virtually how it looks like. So we have this cartridge there. There is two ways of reading. On the top, we do the analysis and we can read, but there is also an extra way of reading the cartridge, the results. On the side here, yeah, okay. So the cartridge you insert it there, or you can read it up there, okay, as well. Okay. And there are some specific features that are quite nice. This is one of the cartridges, okay? These codes allow us to know when we are reading in the downside if it's well inserted, because this is very important in order for us to read. If I say something wrong, please correct me. Here is you have the reagents, you know. Now we have a color liquid because we are testing this, how it's working, how it's reading, etc. But in the future, it will have all the reagents related with the analysis. So all the buffers that we have for the DNA purification and extraction, all the reagents that we need for the amplification. And then here is where we control the workflow. So what is the temperature of the Peltier to heat up the samples and to do the DNA amplification? Yeah, the RGB sensor. So we have an RGB sensor that is also connected with the final part. What is the volumes that we have to insert from the different reagents, etc. Okay, and these are the tubing that is introducing the different reagents onto the cartridge, and this is happening on the top, if you might remember the initial design. Okay, so you see here, yeah, this the procedure happened, and you can read also here. You have a camera that can check if it's well aligned with these small QR codes. No, it's a QR code. You can check if it's well aligned. You can check the color, and you get a RGB coordinate that allow us to, for example, compare to different samples. That allow us to, and this has also, you have all this data that you can integrate on a data flow, and you can integrate onto, it could be a block on the blockchain, no? And this is how we envision this, okay? That this could be brought to different areas of the production. All the analysis could be done in these cartridges with this equipment. The cartridges are disposable, so we avoid the contamination. And then this device can have these RGB coordinates that will be linked to each specific cartridge, and this will be linked to the specific product, so the specific raw material or the specific olive oil or intermediate product that we want to analyze. Okay. Then I don't know how is the time. Okay. So now, what is next, and what is the next steps for this? So as I was mentioning before, now we just started actually an European project, the Titan project, that is to provide digital technologies, to develop further digital technologies that could improve transparency through the food value chain. And this is related as well with food fraud, with traceability of food products, and so on, right? It just started in the 1st of September, so I'm not presenting the results of this, I'm just introducing the project, let's say. We are 27 partners from 14 different countries, and the idea is to work in different areas to increase the transparency in the food chains, from the producer's point of view, but also from the consumer's point of view. Okay, the producers, they have this transparency, so between them, so I know what I'm really getting, I'm sure what I'm really getting, and I'm sure what I'm selling, and then the consumers also have this, better information, because one of the main concerns of the food industry nowadays, and the European Commission as well, is the lack of trust from consumers. No, each small event that happens, even if it's something quite isolated, creates a lot of concern on consumers. Plus, as well, there is the social media scams and so on that sometimes they are not as informative, or they are not as trustful as one might think. No, and there are a lot of these cases of videos of plastic food and things like that are not. If you are in the field, you realize that are completely not reliable at all. Okay. So in this project, we are working with the New Fork, that is SME from Netherlands, that they have their own blockchain technology, this open food chain. I'm not going to go into details on this open food chain. First, because I don't know the film in particular, and secondly, because we will have Marike tomorrow talking in detail about the open food chain, that is the platform that they are using to connect the different food products to the blockchain. Okay. But an important point from their technology is that, as we have been listening related with blockchain here, the intention is that, how it's working now, there is mainly paperwork, or even if it's like digitalized, but it's a very, basic and easy to adulterate type of documentation and type of transfer of information. And the claims that are made sometimes are not so easy to trace back. Okay, so they want to develop a system that is more efficient, so you can have these different blocks, as we saw in the previous presentations, that are not that cannot be altered. So, and everybody has the same type of information. The different producers in the food value chains, the retailers, they have all this information, and they can access it, and they can make sure that what they are selling, what they are buying, is actually what is in the label. No? As you can imagine, our device is just one small part of a bigger network of information and sensors. No, is an approach that will allow us to evaluate. Okay, what is the best way to do that for sensors that are quite advanced themselves and quite complicated themselves. Another good point of the open food chain is that it's interoperable and scalable. So interoperable, sometimes the platforms or the blockchain systems do not talk within each other. And that is something, important, because imagine that you are selling your products to a retailer and it has their own blockchain, but it cannot read your data, no? That's an issue. They have something that is interoperable, so potentially you can communicate different type of blockchains between themselves. So imagine that there is a cooperative that is that has the olive varieties and it has their own controls, and then there is the producer and it has a different one, but then they can talk with each other, they can exchange this information, and they can build a bigger system, okay? And the idea is that to be able to make analysis in the different points of the value chain and include this in the blockchain so that we will have this information. So we have tested that the varieties the varieties from the tree during the harvesting, the varieties before the milling, what it was transported to the industry or what is on the retailer, they are, checked and stamped and certified, if we can say so, as the authentic ones, okay? And then we can add this to the blockchain, and potentially the consumer can also make sure that what they are buying, what is in the label is actually what they are buying, okay? And just to finalize, just to thank my team, of course, that all of them has been involved in different steps of this work, but particularly on the DNA extraction has been Joanna, and the amplification has been Joanna, Shambavi, and also Sarah. And the devices, the initial devices were developed by Andre, and then Agnes was also involved in the detection. And then, of course, to the tech group here from Arena that is developing this very fancy device that we have now. And the new four that will be our partners on the blockchain arena. And if you have any questions, just feel free. Okay, thank you very much.
Thank you, Marta. Yeah. Any questions?
Just more curiosity. So probably I missed some points, so if I missed, just correct me. On your prototype, the cartridge includes the sample and some other sample preparation stuff, or is it only the sample?
It includes the sample preparation step as well. Yeah.
Okay. So you have the cartridge. You have all the materials that you need to extract to the.
Exactly. Yeah. We need to do the initial. There was the pre-treatment initially, so we need to separate the aqueous phase from this we need to do outside the cartridge. But then the cartridge, we are working now in the integration actually, but the cartridge includes the DNA purification part plus the amplification and the detection, of course. Yeah. Yeah.
I have more curiosity.
Yeah.
How long did it take to build the equipment, so from the initial phase of designing and conception until actually having the equipment ready to use?
We had a first prototype ourselves in the group with one of the team members that had built as soon as we were, giving some indication and driving him a bit crazy actually. And it took, I would say, maybe 2.5 years, something like that. And then in the tech group, I don't know, you guys, maybe 11 months, something? Yes.
Working on the prototype.
Yes, there, yeah.
So we were running 3 projects during 1 year, so I would say 1/3 of the year, about 5 people.
Yeah. So it's very challenging. That's why I call it advanced, because there are so many steps that could go wrong that you have to, everything has to fit. That's why, normally we work in modules. So we work with the modules of the purification, and then we work with the modules of the amplification, and then we integrate everything when we know which is the best protocol, which is because it's quite challenging, and they also integrate this RGB detection and all this camera and so on. So
basically, we were merging lots of technologies. Even on the mechanical side, every
Yeah.
single piece was developed from scratch. The resulting pump was done from scratch. The voltaic selectors,
Yeah.
the syringe pump, they were all done from scratch to be optimized to meet, let's say, power requirements. One of the other prototypes we were doing, we only had power from USB, so everything has to run on USB powered. The Peltier heater, it was simulated, so we have all the finite element analysis of this heater. So everything was developed from scratch and then integrated on the computer vision part, and then we were merging a lot of technologies here. So software development itself running on the tablet, computer vision running on top of this software, and the software is basically the host controlling all the mechanical elements present on the system. The computer vision, when we started, we were, let's say, not really, we were confident that it would work, but we were putting our let's say, bets on the other RGB sensor. But in the end, we figured out that on the cartridge, if you have, let's say, a bubble of air in the final, the RGB sensor will fail because the light, so you have a light source on one side and the photo detector on the other side. But if by any chance the air bubble is on the wrong place, the reading will miss. The computer vision is completely agnostic to that, will give you, on top of that, an increased confidence level of the reading. So in the end, the computer vision is quite robust, and in fact enhancing a lot the system. On the cartridge, another effort that was really tough for the mechanical side was the pinching element. So the cartridge is completely standalone. There is no tubing. There is no need to be. The idea is to minimize the cost of the cartridge if you target this for production. So you have a piece of, let's say, plastic, and then the unit will pinch this unit and will take care of all the microfluidics. So you don't need to tube extra tubes. The idea is to have a contained system that is very easy to use from the user perspective.
How long it takes to analyze a sample?
So
yeah. We are aiming to be less than 2 hours, but for the moment it's not. We are not still there, but we are aiming to have less than 2 hours. So something that is useful, you know. It's like, okay, I received that, then, you know, I have it there, and I don't have to bring it to the lab to make sure that what you are telling me is the right thing. You know, it's something that you can check. And it's very important what they are doing in terms of that the system is robust and, you know, avoid all these things at the bubbles and so on. Because the idea is that somebody with a minimum training will be able to do it. No? This is our aim. And also the pinching part, this is really, really nice because we have to avoid contamination. Since we are doing an amplification, if we have any remains, any traces from previous analysis, it will be there and it will be amplified, and then we will have a false positive, for example. So this is very important that everything is contained, is just pinched when we are going to do the analysis, and is going in, you know, the right flow, let's say. And basically this.
Following this, on top of the software has kind of different levels of usage. So kind of in engineering mode, you can set up the recipes, how much time you will grow, let's say the length amplification will occur, how much time you need to heat the sample. You create your own recipes. Then you can pass these recipes to a user level, and the user will only have to select what recipe to execute and press play. So it's completely agnostic to the final user, these small details, how much you pump or how much you heat. So this is, let's say, on the research part, and then you wrap this recipe and you deliver it to the final user.
Yeah.
The software is prepared for that purpose.
Yeah.
Just a quick question about the detection system. So what do you mean about computer vision? Take a picture of the
camera, real-time camera capturing.
But how do you measure that intensity? You select the.
That's why there are some color reference on the cartridge. You saw the markers, and there was some RGB printed colors on the cartridge, and those are used for compensating the variations you may have during this computer vision measurement. So there is a reference printed on this cartridge, let's say a sticker with the markers, along with the markers, that I use to correct the fair right?
Yes.
I use to compensate.
We measure the color distance. We try to have a stable light environment because the box is closed. But even if you have a different source of light outside, and in the case of any variance, we have a reference of RGB and white printed on the marker. So the computer vision system will look at the markers to detect the positions of the poles, and then we'll compare what it sees on those colors and compensate what it sees, what is seen in the holes.
That you measure only color intensity. The signal is only.
We have also this confidence, so imagine that the bubble that you are looking at, this region of interest that the camera is looking as an air bubble inside, right? So the RGB sensor will fail because it will shine, let's say, on this air bubble. The computer vision will give you how much area, let's say, how much this volume is filled with this liquid, and it will, let's say, even tell you the percentage of the filled container, let's say. The output will be attached to this. Basically, the idea is to give you more confidence on the readout.
Yeah, I'm wondering just, and I believe that you already compared that. So, for example, if you use like multiple RGB sensors versus the computer vision, what is the complexity level that you have to add to have this feature implemented? It's very complex in terms of the work, or is that is simple? I'm not, of course, I know that the output will be much better the way that you are doing. It's just a matter of
When we started, as I mentioned, we started with both approach. The validated technology that was before was in fact using RGB detectors, let's say, and a light source on the other side. And by the time I entered, I had even light pipes or fibers collecting light. But in this approach, we dropped the fiber optics because of the mechanical assembly is very bad. We put individual RGB sensor for each light source, and we only turn one at a time to avoid cross-contamination in the sense of light going. But in parallel, João was working in this computer vision approach. The tablet was there, the processing power was there, and basically it was João's effort to put on top to validate this approach. And the conclusion that we have so far, this is still being tested, is that computer vision has superior output compared to.
I agree that will be much better. Just wondering about. Okay.
In the end, it will save hardware costs on you. So the tablet is there.
Yeah, you have the power there, so it's okay.
Nowadays, these chips are extremely inexpensive, and the idea is to avoid extra costs on the hardware and to have a more robust readout.
And the system is intended to be quantitative or just
No,
qualitative?
just qualitative, yeah. We could try to make it quantitative, but at the end what you want to prove is that the varieties that they are saying are there. So we will focus for the moment in just few varieties, and then some extra varieties that could normally use for adulteration, because they are cheap, they are very efficient in production, are not there. So, yeah. So we just know, let's say. Yeah.
Thank you.
Okay.
Any other questions?
I have another one, just for curiosity. In
Yeah.
terms of eco-friendly, you use plastic.
Yeah.
Does anyone ask you, like, if you have a possible alternative for those things? Because in any sample, you will use a new one, right?
Yeah.
So,
Yeah, it has to be disposable. This is very important because of contamination, and this is actually a very good question because it's an actual problem, no? I mean, for the moment, we are working with cartridges that are prototypes, so they are PDMS, PMMA based. So yes, plastic, not so eco-friendly. In the future, when we think about scaling up, the materials might need to be changed, because it's PDMS for scaling up mass production is not ideal. Yeah, and yeah, we should find an alternative. We are working in other projects with paper-based, Imai's there, but with microfluidics in paper-based devices. And this is really something that we are aiming to still working on because it's very, very interesting, it's very cheap, and you know, gives you a lot of possibilities as well. So, yeah.
Sorry.
Yeah.
Following this question about not reusing the cartridge, won't that also imply a big cost? Because if you are testing at all of the steps of the chain, you will always be using a new cartridge. I don't know if it's cheap or not, but for now it's still...
It's still expensive. Yes.
Like a lot of them, won't that imply a big cost in the end?
Yeah, I mean, it's not cheap. This I must say. We are aiming to try to, you know, reduce prices. The advantages, for example, of using microfluid is you can reduce the price because you have less volumes, but you know, set everything there. So yes, it's not ideal still, you know, but yeah.
Yeah, of course, I understand, but it's like a really nice technology.
Yeah, I mean, we are trying to kind of balance the usefulness, let's say, and you know, to approach something that is normally. I mean, if we think that the producers that probably are not doing this, you know, in most of the cases, as maybe at the end, maybe the big producers, they have to send the samples to the labs and pay for the analysis and everything. Yeah, it compensates, and they can control themselves, which is good, you know. Sometimes they commit fraud between brackets without knowing, you know, because there are a lot of, like in Portugal, in Galicia, in Italy as well, there are a lot of, there are areas where big producers, but there are other areas with small producers, so they gather together, so they have different, you know, they have all the documents, fine, but sometimes, you know, unintentionally even, there is mixture of varieties or, you know, we were talking with some company we collaborated with, that they have like how it's called? Hatchery? No. Like a vivero? Like they produce the baby plants, no? I don't know, I forgot the name in English right now. So they have the baby plants, let's say, to sell to the producers, and they have problems to make sure that, you know, they are selling, I mean, what they are selling is the correct one, you know? As they were telling me, you know, sometimes we have to wait until the plant, because, you know, the systems normally is still very visual. Not everybody sends to sequence the plant, so yeah, yeah. Okay.
Okay, so good morning, everyone, and welcome to the third day of the summer school. So I introduce today, sorry to replace Nuria. I'm not as good as she is, but yeah, I'm trying to explain. So today we will have a few scientific lectures. In the morning we have really pleased to welcome Professor Federico Marini from Università of La Sapienza in Rome. He will introduce us to a few concepts related to data analysis in the chemical sensor and for chemical data in general. So yeah, he will guide us through a few introductory slides, and then we will have a focus on data fusion, so fusing data from multiple instruments or multiple sensors. And yeah, later we will have the presentation from Marta, and in the afternoon another invited lecture from a speaker from Wageningen on machine learning and digital twins. Was good, okay. Yeah, so I give the floor to Federico. So if you have any question, please don't hesitate to ask him. He's really kind and was really kind to accept our invite. So thank you, Federico.
Well, thank you for the introduction, and thanks for the invitation. I mean, it's a pleasure for me to be here and to do these things like in presence. So I was asking actually briefly about the background, and if you have seen, I've just added like some slides to the presentation that I had in mind, because not knowing how shared was the background about data analysis, I was thinking that it would have been beneficial to try to set up a sort of a common language. So of course, if for all of you what I'm telling in the first slide is too trivial, just tell me, because I can easily skip it. But I was thinking that speaking about generalizing PCA, PLS methods to the multi-sensor, multi-block case without anyone knowing what a PCA or PLS is would have been a bit awkward. So, okay. So I will start from the very, very, very beginning, but you will see that we will go very quickly over these first slides. So the thing is that, of course, we in general, well, I speak about myself. I'm a chemist. I'm an analytical chemist, even if I do like chemometrics full time, and I work mostly in method development. But of course, the good thing about data analysis for let's say, chemistry, but not only chemical data, so what we call chemometrics, is that, of course, we start from the data. So our statistical tools, our data analytical tools start from the materiality of the experimental data. And of course, we will see and we exploit generally the equivalence between measured data and geometrical representation of the data in order to get an insight that is as straightforward as possible. But in order to do this, of course, we have to set a bit the scene. And the scene is that, for instance, when we measure like experimental data that could be like this in the form of a NIR spectrum, so a signal that is recorded, in particular in this case a reflectance intensity recorded as a function of multiple wavelengths, we have, first of all, a direct equivalence to a data table, so what we would call the matrix. And then from that, we would see that there is a further equivalence between a data matrix and directly geometrical representation of the matrix element, or what we would call the row space representation, because any of these rows of the experimental data matrix would be corresponding to a point, to a vector that means a point in the multivariate space. And of course, like, we will exploit this geometric equivalence in order to make consideration about the system that we are investigating. Here you see each sample, each experimental profile measure on a sample would normally be represented in terms of a row of this data matrix, where each element would be, for instance, in this case, the reflectance, or here it's pseudo-absorbance of the sample at the different wave number. You see it here, I don't know if you can read, but it's the logarithm of the reciprocal of the reflectance at 4,000 reciprocal centimeters, 4,004, and so on. Of course, if we measure multiple samples, we will end up with multiple rows in our data matrix, and we will end up with a complete data matrix whose rows corresponds to the profile for each sample, and whose column corresponds to the individual variables, experimental variables, like measurements that we do on the different samples. As we will see, the idea of data analysis has to do with trying to get as much information as possible from the measured data. And the idea would be to try to grasp some similarities and dissimilarities among the sample if we stick to what we would call an unsupervised analysis. But later on, of course, it would be to use these measurements to predict in a possibly rapid way properties, one or more properties about the systems that we are characterizing. And one way of grasping rapidly, because this is something that we are very able to do with our own eyes, similarities and dissimilarities between samples or observation or entities in general, is the possibilities of visualizing the distribution of these samples and their reciprocal position in a multivariate space. So how do we do it? The thing is that, as I was telling before, we exploit the fact that when we have a data matrix, by its own nature, a data matrix has a direct equivalent geometric representation in terms of points in multivariate, let's say, multivariate meaning with a high number of axes space. So each row of the data matrix, so each sample, would be characterized as being a vector, or finally a point, in a multidimensional space. The number of dimensions being strictly equivalent to the number of variables that I measure. So for instance here, if my spectral variable are like 4,000, or if I'm measuring absorbance or pseudo-absorbance at 4,000 wave numbers, then I will end up with a 4,000 dimensional space. Of course, you may understand that for the sake of making a clear visualization here, I had to stick to the simplest case where the number of dimensions is 3. So here, you have seen in this case, I was taking a mid-IR example where one column was the absorbance of 1250 reciprocal centimeters, the other one 1710 reciprocal centimeters, and the third would have been like what I put 2890 reciprocal centimeters. But this is just because, of course, I cannot draw, I am not able to draw, and you are not able to visualize 3,000 or 4,000 dimensional space. But the idea is that each of the column of the data of my data matrix would give me a coordinate of my point in this multidimensional space. And here, of course, we go to the main issue that we have, well, with the main issue. One of the main issues that we have when we want to do efficiently our data analysis. Because if we want to exploit, so let's stick for the moment to the case where we want to understand the characteristics of the system that we are investigating. So it means that we want to understand whether we have similarities or dissimilarities between our samples. Well, this is something that I didn't tell explicitly before, but if you think about it, since each of these dimensions has a direct chemical or biochemical or physical interpretation, because these are measured quantities on our data, then if I have similar values of these variables, so if my points are closer in space, the direct translation in chemical terms of this is that my samples, they have similar chemical properties, because they have, for instance, a very similar spectrum or a very similar electrochemical response and so on. So if I can get the possibilities of checking which points are closer in space and which points are farther in space, then I have an immediate and straightforward first information about the similarities and dissimilarities between my samples. And not only that, of course, because if I check, for instance, that these samples are closer along this direction and farther from the other sample along the other direction, then I can also, let's say, interpret in chemical terms why these samples are similar and dissimilar. And this is exactly what constitutes the core of what we would call an exploratory data analysis. So the moment when I, with a very, let's say, anthropomorphic representation, I let data talk. So I let data without any external, that means of myself, intervention. I just see, like a photograph at a bird's eye, I just see what the data are telling me, as they are. So what are the characteristics of the measured data? So far so good, but you have to understand that at a certain point, we have a slightly tiny difficulty. That whilst we are very good in looking at 3 dimensions, unfortunately, we are not as good in checking and looking in even 10 dimensions, but considering that our data normally have 100 or 1,000 dimensions, then the problem becomes a bit difficult to tackle. So you will see that most of the method that we use, not only for the exploratory data analysis, but we will see also for the predictive data analysis. So that means when we use the outcomes of our sensors to predict a property that, for instance, otherwise would have been more difficult to measure, or even cumbersome, or even lengthy and costly to measure. I mean, if you think something that, I mean, we are in the context of food data, so something that it's very easy for probably for most of you to understand, measuring proteins. So measuring proteins on a flower or on a food sample means enacting, for instance, a Kjeldahl system. So I have to take my sample, I have to mineralize it in very strong acidic condition, neutralize, distillate, collect the distillate, and titrate eventually. So for one sample, not speaking about the amount of reagents that I'm using, I am anyway having an analysis that even in the micro version would take me at least 3 to 4 hours. Whereas if I'm using NIR to predict proteins, and now this is almost routine in many laboratories, I just take my sample, I don't treat the sample, I just put the flower directly on a Petri dish on the instrument. 1 minute, half a minute, I get a measure, I get my calibration using chemometrics, and then I have an outcome, and protein in the sample is 15%. So, of course, but both in the moment when we just want to characterize our system and in the moments when we want to predict something from our system, then we will look for the possibilities of having a tool that allows us to inspect the relations between the samples that we have. And of course, when we speak about some of these tools, that will be, let's say, the common denominator of most of the chemometric techniques that we will be speaking of, we are speaking of something that is based on the concept, on the general concept of making a projection. That means I have my data in a multidimensional space. Of course, you will see me like resorting to such kind of example very often, because of course we can look tri-dimensional space, we cannot look 10,000 dimensional space, but the good thing about mathematics and statistics of this kind on geometry is that what holds for 2 dimensions holds as well for 10,000 dimensions. So we can be sure that what I'm showing you here is good, even when we generalize to the case not of 3 dimensions reduced to 1 dimension or 2, but to 10,000 dimensions reduced to 1 dimension or 2 or 3 and so on. So what's the idea? The idea, of course, is when I'm doing a projection, meaning that instead of using, I don't want to kill myself, instead of using like the whole variable space to describe my samples, I use the possibilities of identifying some privileged, in a way, privileged direction in space where I can project my data. And hopefully, of course, if I am choosing very carefully the kind of projection that I am doing, hopefully I get not only a variable reduction, but also if I am cleverly choosing where to project my data, I have the advantage of preserving most of the information that was originally present in my data. So the idea of projecting the data, you see, this is a tri-dimensional space, and in this case is to highlight, I do the very simplest case, from many to just one. So the extreme synthesis in terms of what I'm doing. What I'm doing is just to capture or like define, instead of using the original tri-dimensional coordinates of my point, just use the coordinate along this direction to summarize the distribution of my point in the multivariate space. So the concept is simple, and what I end up with if I do something like that, and this will constitute the main message that we will take with us across all these 2 hours that we will be speaking together. Well, I have 3 elements. The first one, I start with the disadvantage and then I go to the advantage. So the first one is that if you look at it and you don't see it in an abstract way, if you look at this graph and you think that this one is something that I measure, this one is something that I measure, and this one is something that I measure, the main disadvantage is that if I want to really compress my data without losing information, I have to describe my samples by not using, for instance, one of these measured coordinates, because this would have been cheap. I measure 3,000 variables, I just select one, like I did before in my example. I just pick up 3 random variables of these. absorbance as 1700, 1200, and 3000. And then I use these 3 variables to describe my data. Well, this representation would be plausible, but it would be suboptimal. So we would see, and you see it clearly here, that if I want to capture essentially the distribution of my point, the direction that I'm choosing to summarize my data must pass through the data distribution. And this means that they have to be latent variables. So latent variables, you mustn't be disguised by the definition, just means that they are not directly measurable. That means that if this was the absorbance of at 3000, this was the absorbance at 2000, and this was the absorbance at 1000, this direction is not anything that I would singly directly measure. So singly, individually, directly measure. So that's the drawback. What is the plus, or what is something that could tell us, okay, but life is not as bad as it seems so far, is that even if the direction is not directly measurable, it still depends on measured entities. So I can still do my chemical interpretation. The problem is that it will not be as straightforward as if I was identifying directly these, and these variables, so these, and these absorbances, but interpretation is still possible. So the price we pay is not 0, but not either. What I end up with, these 2 things. When I was asking, I heard that the background is quite diverse, but for some of you, if not all of you, have probably heard about scores and loadings. So this is what we mean. So if I do such kind of projection, the final thing that I end up with is coordinates of my point on these new directions that I am identifying, what I will call the scores. And if you look at the scores plot that I put here, you see that I can clearly identify or highlight that there are 2 groups of samples. So here, think that these were not 3 variables, but they were like 300 variables. Then I do this variable reduction by a way that we will shortly see, at least in concept. And eventually, I can have this kind of plots where I draw the coordinate of my point along this new direction. And I clearly see that if I look at my point, I have 2 groups of samples. Probably here I have 2 subgroups. And here I have this point, this sample here that is probably an outlier or a unique sample among the one that I've measured. And then you tell me, okay, but this is nice, but it would have been nicer if I could have said, okay, I see these differences because there are more lipids here, or let's say the intensity of the 2800 peak is higher here and lower in this group of samples. And then for this, we have what we call the loadings, because here you have the direct geometric representation, because this is something that we can only do when we have 3 dimension and 1. But then let's exploit these graphics that we have. This direction here is associated to the cosines, so the directing cosines of the direction. So I see in the original variable where it points. These cosines is what I call the loading. They tell me, okay, this is the orientation. So if I have to have these variables that are high, you see, I have to point in this direction when these 2 variables are high and this is low. And vice versa for these samples here. So I get straightforward information on what are the differences and similarity between my samples, and also I get a guide that tells me in chemical terms how to interpret these similarities and dissimilarities. And of course, I was just using the simplest example, so 3 variables reduced to 1, but of course, not always I am able to compress the relevant part of my information in only a single variable. Sorry, I forgot to tell you something. There is a third element that's very important to close the circle, that if I am doing such representation, I am also able, and you can see it clearly here, to have an estimate of the residuals. So to have an estimate of how good is the representation that I'm doing, how much information I am leaving under the carpet, how much information I am not taking with myself when I am modeling this data. And of course, if this residual would be too high, no one prevents me for adding a second dimension here. So here you see that the same data distribution, you just see it from a different perspective because it was easier to show it in a planar screen, but this is exactly the same data distribution. If I am adding a second direction, so instead of projecting my data on a single direction, I am projecting it onto a plane, then of course I get a better fit. And if I am choosing reasonably such plane, then I am able to better describe my data. Of course, this is good and easy to show when we have 3 dimensions to 1 or 2, but you have to think abstractly a bit and understand that this is exactly what we can do even when the starting point is with 300, 3,000, 3 million variables. So and I will add something more, but this is more just a quick philosophical consideration. Why we can do it and why these concepts are particularly efficient in the chemical or, let's say, chemical, biochemical, biophysical domain. Because our variables are highly correlated. If we think about the spectral landscape, of course, the intensity, think about the spectral shape, the intensity. For most of the samples, the intensity at a wavelength, they are quite correlated to the intensity to the neighboring wavelength and so on. What does it mean in geometrical terms? It means that these points here will not be scattered randomly over the multidimensional space, but will actually be very oriented in a limited subspace of our multivariate space. It means that when we do this compression, even if our data technically should span 3,000 or 3 million dimensional space, with the exception of a bit of noise, they occupy a lower dimensional space. So when we do this compression, we are doing almost lossless. So we are actually getting the relevant part of our information, and this is the good part. So this concept that actually apply them both in the 2 main divisions of the modeling that we normally use. So in unsupervised modeling, as I anticipated, we are focused on getting our data, and from this data, getting information about the data distribution, the presence of anomalous or outlying observation, the similarity or dissimilarity between samples, and normally we would do this through many instruments, but the main tools would be what we call PCA, or in general, some component analysis that can be not necessarily only PCA, but PCA, principal component analysis, is the most frequently used one, where we just do this projection and observe the data distribution and try to interpret it. And in some cases, we can resort to what is called cluster analysis. That is another way of getting information about similarities and dissimilarities between the samples. The other family of tools, in this case, I only need the matrix with my experimental measurements. For instance, whatever sensor data, spectroscopic, electrochemical, I don't know, thermal or whatever. In the other family of method, of course, what is called supervised learning, our aim is to predict a qualitative or quantitative property, or one or more qualitative or quantitative properties. When we want to predict a qualitative property, we are in the domain of classification. So here you want to use, for instance, the signal to check whether, I don't know, a batch is good or faulty. Or, I don't know, for instance, a barley is harvested regularly or pre-harvested, just to tell something. Whereas with quantitative model, we want to predict like one or more quantitative variables. For instance, proteins in wheat or proteins in another kind of food, or antioxidant in oil, and so on. Of course, if we want our prediction to be reliable, then we have this additional constraint that if we want to build a predictive model, we have to have some set of samples for which we know for sure the value of the property that we want to predict. So here we have to have some samples for which we are sure that we can know the origin, for instance. They come from this region or this region or this region, so that we can actively use this information in model building. And the same here in the case of calibration. So we have to have a set of samples for which we know exactly, for instance, in the example, the value of the proteins that we want to quantitate in the future sample. Okay. Then with these premises, without going much into the math behind, when we speak about exploratory analysis, like the workhorse, the most frequently used tool in chemometrics is principal component analysis. Why? Because if you think about the scope of exploratory data analysis, so what I want to do with my data when I do the exploratory data analysis, that means let data talk. That means compress the data in a way that I can have the most faithful picture of my data compatible with the fact that I am measuring 3 million variables and I can plot only 2 or 3. So then, if you think about what my scope is, then you understand. I will just show this, but I will not go into the end. I will just tell you what this series of equations means in practice. Principal component analysis is based exactly on a least square fitting of my data. So the idea is that I want to compress my data. We have seen the machinery, so identifying one direction or 2 direction or 3 direction in space, that once I project my data on this direction, I have the most faithful picture of my data. Then why PCA among all the possible projection methods? Because it does exactly so. Because I am checking, if based on what I was telling you, I could take one of the infinite direction in space to project my data. So why to choose this direction here rather than this direction here or this direction here? The idea is to look for a sensible criterion to decide which direction to use. And this sensible criterion, when I'm doing PCA, is having the best fit of my data. That means I am looking for the most faithful picture of the data, the one that when I look at this data, leave me as few of the information apart. So that's easy. So this criterion is perfectly equivalent to tell that I am selecting the direction in space so to have maximum explained variance in the distribution of my data. But this is a consequence of the first and ground idea of PCA. So in PCA, I am selecting or identifying the direction in space where to project my data so to have the best fit possible for my data. That means the best unbiased representation of my data, compatible, of course, with the fact that instead of using all the dimensionality of my space to show my data, I'm using just a restricted portion of my multivariate space. So this is for as far as it goes for with exploratory analysis. But then we have predictive analysis. And in predictive analysis, actually, one should make a small, let's say, detour, because I think all of you know like standard or ordinary least squares. And in general, I mean, when we want to fit or predict a y given multiple x, so instead of having a single x, we have more, like a spectrum, then the principle of like ordinary least squares could be generalized. The problem is that when we have a lot of variables, due to the increasing amount of variables, we are not able to fit standard least squares model anyway. So we need to look necessarily for data compression. So normally, what one could tell is that, okay, but you have just spoken like 2 minutes ago that if I take PCA, I get an unbiased compression of my data. Why not using like principal component scores in order to then build all my future models, classification with LDA, linear discriminant analysis, and calibration with multiple linear regression? Well, actually, we could do this, but we have also another opportunity, because we have to think, especially when we are dealing with real data, that, I mean, I didn't go because we have 2 hours and I still have to speak about data fusion, but the thing is that you have to know that when we are capturing most of the variability in our data, that is the idea of PCA, of course, PCA is an algorithm, like most of the algorithms that we will be speaking of. So even if we try to put some anthropomorphic nature to this algorithm, these are quite stupid. They do what we ask them to do. And of course, if I have a lot of variability that is not related to the property that I want to predict, for instance, if I want to calibrate protein amount in samples, but I have a high variability depending on whether I take this variety of wheat or this other variety of wheat, and moreover, if I take them that are cultivated in Sicily or in Central Europe or in Portugal, and so, of course, I am bringing the highest variation, so the variability that characterizes my data can mask the variability I am interested in. That means the effect on my, for instance, spectroscopic signal due to the decreasing or increasing amount in protein. So if I do first PCA, where I capture most of the variability of my data, it can happen sometimes that this variability may not be related to the property that I want to quantitate. This is why we have alternative options for doing data compression in the moment when we want to make not only exploratory analysis, because with exploratory analysis I want to see what's in my data to cool. But if I want to predict specific properties of my data, that means specific responses, then I may want to use this information in deciding where to compress my data. And PLS, that means partial least squares regression, that is the other workhorse of chemometrics, is actually based on this concept. I mean, here, behind the math, you just have to focus on these 2 lines here. The rest is machinery. It tells you how to do it, even very briefly, because it's a very compact description. But still, I mean, you can just forget about the main part of the slide and focus on the first 3 lines of this slide. So you think about the same case as before. I want to project my data onto a reduced set of scores so that I can use this, in this case, not only to describe my data, because I still have this property. I can plot my scores and I can see, for instance, if my calibration set, so the set of points that I'm using to build my model, spans regularly or homogeneously like the sources of variability that I want to describe. So I always keep this property, but I have an additional property here. So I can decide that instead of projecting my data in along this direction, because this direction fits most of the variability in my X profile only, so only in my spectra, I can have a compromised direction that probably doesn't fit all the variability in X, but is most effective in predicting my response. So instead of projecting my data here, I'm just tilting it a bit to capture also a part of the variability in Y. That means that I am sacrificing the possibilities of explaining a part of the variance in my spectra, but I'm going more effectively in predicting my properties. This is the essence of PLS. That apart from that, they share the same characteristics in terms of being able to calculate or estimate the residuals, having an idea on how good my data representation is, plotting my scores, allowing me to check, for instance, if I have subgroupings within my data. For instance, if I don't get a nice fit, I see that my model is fitting. For instance, I get reasonable predictions of my proteins, but reasonable means good but not optimal. Then I may have a look at my scores distribution. I don't know if I have a plot here. Well, let's see like this. A score can be the same. And check that, for instance, I have subgroupings, like here, clusters of my data. Then I may think that it could be better to adopt, I tell it it's a local approach. That's the sense that I could think that probably I should fit a model for these samples only, a model for these samples only, and a model for these samples only, and having more effective predictability of my property or my properties of interest. And the good thing is that this concept here that applies for the cases where my Y is quantitative, so like it is real value, could be easily generalized because I have similar problem when I am dealing with multivariate data for the case where I want to do classification. So when I want to use my profiles not to predict quantitative variables, but a qualitative one. We have a tool, in this case a standard tool, it was dating back by 90 years ago by Fisher, that is called linear discriminant analysis, that is aimed at doing exactly so. So taking an experimental profile and telling, okay, based on this, I have this kind of samples or this kind of sample. Here I put different examples with two classes, two values, healthy or diseased, or three classes here, like high activity, low activity, and medium activity. This could be like four, like wines coming from Portugal, from Italy, from Spain, and from France. So the important is that the answer is discrete. So it doesn't take, it takes a number, a numerable number of values that are not continuous. Then if I am using standard tools like the one that I mentioned, this is called linear discriminant analysis, with many variables that are also correlated, I end up in the same problems that I had with least squares in calibration. So I'm not able to calculate a model mathematically. So even if I have a nice theory, then when it comes to having a model or model building, I cannot build my model. And the good thing about this framework is that if I am using a suitable coding, and this coding is a binary coding one, so for two classes it's just 1, 0, for multiple classes it's just 1, 0, 0, 0, 1, 0, and so on, then I can apply PLS to this data, do the data compression, and then, for instance, use discriminant analysis or putting a threshold and do my final classification. This is what we would call PLS discriminant analysis. So far, this was trying a sort of recap, or let's say setting the scene for standard chemometric tools for the analysis of sensor data. I don't know if you have questions so far, if I was too quick, too slow. I don't know. You tell me. Yes?
I actually have, for the PCA method, I think there's always some outliers. Or
Yeah?
So how
Well, always not necessarily, but there can be, yes.
Yeah, how do you do that? Like for the normal distributed data or non-normal distributed data?
Okay, so then Okay, so let's say that outlier identification is always a big problem. So actually, it would deserve like not just 2 hours per se. But let's make the long story short. So with outliers, we have 2 main approaches. One approach is to detect outliers and remove them. The other approach is to try to make our model as less sensitive to outliers as possible. So it depends on what is your aim. And you have also to think that sometimes what we identify as an outlier could also be simply like the effect of undersampling. So we always have to be cautious. So let's start with the simplest part. In PCA and in multivariate analysis in general, with respect to traditional approaches, you have actually 2 ways, and in regression even 3 ways to define an outlying observation. Because sticking to PCA, you may have an outlying observation because when you do the projection, you have too high residuals. That means that your compression model, your PCA model, fits very well most of the data. Let's say that the average distance between each sample and the projection on the PC space is certain value. And you have one sample that is fit not that well. Let's consider a real-world example. You have your system where you have a certain number of components, and then in one sample you have a different constituent, one more or one less. Then this is something that would normally, in practical cases, give you such sort of high residual. So that's an indication. Then you have to decide what this is telling you. But the good thing is that there is something called a contribution plot. So actually, you could trace back why that particular sample is outlying with respect to this high residual. So you could check, for instance, all this area of the spectrum as an intensity that is lower than explained by the loadings. So this means that, for instance, like this constituent is absent, this interferent probably, or relevant constituent is absent only for this sample. Then you can decide what to do with it, because then you can just also decide that you want to take it. Similarly, we have a second way of having an outlying or abnormal observation, is that in the score space, so when you look at the projected data, then you have one point that is far from the other. And also for this you have a measure, it's called T-square statistics, that is actually based on assuming a sort of a Gaussian distribution of the scores. There are ways to do it non-parametrically, but this would take even more to discuss. But there is a way to go away from Gaussian hypothesis. There is also the thing that by the central limit theorem, you can think that scores are more normal than the original data, so you are sort of safer in this way. And also for this, you can decide whether that observation is really anomalous or not by looking at this. They are called contribution plot. They just break down this abnormality value into the contribution of the individual experimental variables so that you can check where the abnormality goes. So one advantage of this is that if you do it properly, you have not only the red light, this is a suspect outlier. No, you have also an indication of why this observation is a suspect outlier and along which part, residuals or scores. And of course, in calibration, you have also the third direction of abnormality, a point that is fitted not well, not in the X, so not that the components are not explaining well your data, but you have a bad prediction. So the Y is also fit not well. So this is one way. The other way is to use so-called robust methods. Robust methods are methods that take into account the possibility that in your data you have a fraction of potential outlier. And actually, Indeed, they are characterizing by a property that is called the breakdown of the robust method. That means the highest percentage of outliers that the method can tolerate. Well, okay, it's the opposite, because it's the highest percentage of the lowest percentage of not outlying samples that the method can tolerate. So a robust method with a 75% breakdown means that it can tolerate up to 25% of outlying observation. So of course, like anything, you have to choose the methods and the model that you are that gives you the answer that is closest to what is your scope. So you want to detect outlier, you want to detect anormality, or you want to build a model that, not knowing if any of your observation can be an outlier, can still be applied and can still work practically, even if among your calibration data there could be a part of data that are possibly outlying. You do the choice. Are there any other questions so far? Yes? Yeah.
If you have to predict, for example, 3 variables instead of 1,
okay.
do you use one single PLS model?
Okay.
For 3 variables?
So we are going to the difficult questions. So for those of you who are not familiar with PLS, I have to make just a step behind. So with normal standard least square fitting, since you are not assuming any structure, I mean, you are not assuming any possible correlation between your responses, your Y, then of course, modeling a single Y at a time, or modeling all the Ys together. For instance, I take my NIR spectra and I want to predict moisture, lipids, starch, and proteins. Real example, one of the standard data set that are used for benchmarking in chemometrics, just to make something with reality. So if I am taking like standard least square fitting, ordinary least square, if I am modeling, I am using my profile for modeling a tetravariate Y, so all the 4 Ys together, or a single Y at the time, I get exactly the same model. So I get exactly the same result. So my regression coefficients, so the values that link my Y to the X, they would be exactly the same. With PLS, actually, you have seen that I am trying to look for scores that take into account directly the Y. And I wasn't entering very much into the machinery of that, but the idea is that I am also extracting components from the Y. So if I have more than a single Y, I am summarizing my Y using some sort of principal of scores as well for the Y. So he was asking me, that's a very debated question, what happens with PLS if I have to model more than one Y at a time? So should I do a single Y at a time, or should I model all the Ys together? Well, the answer is it depends. Okay, in this case, I can give you a recipe. So it depends, yes, but it's not completely abstract. So the thing is that you think that you get something more if you exploit correlation. So the idea is, if your Ys are correlated, and this you can see it very easily because you take your Ys, for instance, these 4 Y, starch, protein, moisture, and and lipids. You do a PCA on the Y, and you see the distribution of variance, or you see the scores plot and the loadings plot. If the Y are correlated, then it could make sense to build a model with all the 4 Ys together, because you exploit this relation between the Y to increase the prediction of the Y itself. If there is no correlation, then it's useless to make a model with all the Ys together, because actually you are also you can have that, for instance, you need 3 components for fitting the moisture and 7 for fitting the proteins. And then you are sacrificing a bit one towards the other, or you are taking a overfitted, like a too complicated model for one, or you are sacrificing a bit the predictivity of the other. Of course, life is always more complicated than mathematics, and you have intermediate solutions. So you can do the PCA on your Y, and looking that, for instance, you have 2 very highly correlated properties and the other 2 that are unrelated. Then it could be beneficial that you model the 2 correlated properties together and you model individually the other 2. Other questions? Okay, so, I don't know. Should I continue or do they do a small interval? How does it go?
Maybe we can do a small break of 5 minutes and then let's take some water.
Yeah.
Yeah. Then the other break is at 11:30.
I'm going to move to hip hop for teaching. Well, I have some chemometric songs on YouTube, so yes. And even there is also one with the piano.
Exactly.
I even played it during the conference.
Yes,
didn't I?
yes.
Okay. I think it's everyone. No, we have to wait for some more people. Okay. So we can start with what was the core part of my talk, that would be fusing the information from multiple sources. So what we would call data fusion, and in other, let's say, you will find also, well, especially in terms of the models that are used, you will find it also expressed as like multi-block methods. So of course, I mean, since this was the decision according to which I was invited to speak here, I don't have to spend much time about the rationale behind fusing multiple information. So the idea is that we would normally have multiple sources of data, multiple sensors. Here I put an example of different spectroscopic and a thermal analysis technique used to characterize beer samples, so a very important problem, to authenticate one craft beer produced in the surrounding of Rome with respect to other competitors. And in these cases, of course, like we have quite clear in mind what the different blocks of information that we want to combine are. But since we will see that there is an advantage in general to exploit blocking within the data, we have to think that in some cases, even when the availability of multiple sources of data is not so evident, like in this case, we can still induce some blocking in the data, either artificially or like based on some reason. So for instance, this is the case of a profile that we would normally analyze altogether. This is MIR spectra, in particular, like acquired using an ATR module, but this is not essential for the moment. But of course, we could think normally, what we would normally do would be to take this data and analyze it either unsupervised or supervised as a whole data matrix. But we could think that it could be beneficial to divide this data, for instance, according to some chemical-based division, in this case, by taking separately the fingerprint region and what we would call the region of the group frequency, so more or less approximately everything below 1500 and everything above 1500 reciprocal centimeters. And for instance, for those of you that are familiar with near-infrared spectroscopy, a similar consideration could be done, for instance, by taking the part associated to the combination band. That means everything that in terms of reciprocal centimeters is below 5200 more or less, and the part of the overtones that are all the intensities, all the wave numbers that are above like 52, 5300 more or less. And we will see why. Of course, this is an example that is grounded on chemical principles, so on the principles that govern the absorption and of the light in this region. But we could do even the same reasoning just by deciding that I want to take my profile and divide it into, I don't know, 5 regions because it can be useful. a colleague of mine, well, not in the sense, I mean, a professor from France with which I have cooperated, Doug Rutledge, decided to make this thing even extreme. So actually, he devised a variable selection technique based on multi-block idea, where each variable was a single block of data. Okay, this is a bit extreme in terms of speaking of using the data, but let's say that something in the middle would be reasonable. So, of course, time is a tyrant, so I will not speak about all the possible way of using the data, but you have to think that you will see that in general, all my example would be concentrated to the case, well, the multiple data matrices or the multiple data sources that we want to combine, so based on which we want to exploit the relationship, they will share the sample direction. So we will focus also, because this is the situation that is more closest to what could be of interest for you all here. The idea is that we will focus our information to all the cases where the direction that is in common between the different data blocks is the sample direction. So multiple platform sensors that are used to characterize the same set of samples. So I will not stress much that again in the presentation, but this is the case that we will be considering so far. But of course, there can be cases, for instance, in other applications, also useful, for instance, in the domain of food quality, food authentication, where the variable direction is the one that is shared between the samples, between the matrices, sorry. And one, let's say, paradigmatic example is the case of batch processes. So where we are considering different batches in which the variables are followed across time during the whole batch lifetime for the particular production process. This is another case of multi-block data, but it's a case that we will not be considering further. So, of course, I mean, I try to, especially when I have to concentrate my teaching or, let's say, description on a very limited time, I first try to give a general overview, because then that sets the scene and gives you some coordinates to try to interpret what we will be seeing. So, and in this case, the idea is that we can organize mentally the different models that we have available depending on several characteristics. The first one actually is in the directionality of fusion. So, of course, when I have different blocks of data, I have to understand whether all the different matrices are on the same level or not. So, if all of them have the same role or not. In terms of data fusion, if you want to tell it appropriately, this means speaking about symmetric or asymmetric fusion. If you want to, let's say, scrap a bit this definition, symmetric fusion is normally when I am doing unsupervised analysis. It means that I want to understand the relationship between all the different data matrices, and all these different data matrices are on the same level. So I want to understand all possible relations of these matrices between one another, among one another, sorry. And whereas in the asymmetric fusion is the case of predictive modeling. It means that my idea is that not all the blocks of data are equal, because I want to use, for instance, n-1 of these matrices to predict the one that is left out. So normally, this is the case where I am using multiple X matrices to predict one or more property of my samples. Well, in the field of, especially in the field of food, consumer science, there are also some peculiar way of using the data that I will just tell you. I mean, I will just tell them to you so that you know that this is possible, and if some of you is interested, can go to exploit or check particularly this kind of fusion. This is where the relation between the blocks assumes a particular geometric shape, in the sense that, for instance, I have that two matrices are linked along one direction, and two matrices are linked according to other direction. And this is the case, for instance, of this problem here. So if you want to know, this L-shaped fusion was developed in the beginning of year 2000 in the context of consumer science. So because in that case, there were some characteristics of the products that were assessed on one hand by consumers, on the other hand, the products were characterized by panelists and by measurements. So you could put all together different informations about the data. So this is sort of a summary of what can happen in the simplest case. It means when we are dealing with data matrix or data matrices, in order to understand what could be the configuration, the data configuration that can occur. And the first one could seem a bit awkward to you. So I have here neither the sample nor the variable mode. So you can look at me and think, okay, so are we still speaking of fusion in this case? Actually, this I wanted to leave it to you because it allows us to think a bit out of the box. Of course, if you are here and you are listening to me, okay, apart from the fact that you are partly obliged to do it, but then let's think that we understand that we are speaking about statistical fusion of our information. So actually, so far I give it, or I left it a bit untold, but our idea of fusing the information means that we want to incorporate in a single model the information present in the different blocks of data. So we are using modeling, for instance, our generalization of PCA and PLS tools that's why I was speaking a bit about them before, in order to incorporate the information from the different data sources onto a single model. But of course, there are other ways of fusing the information that are less straightforward, a little bit more arbitrary, but that still exist. So in this case, and this is why I was leaving it to you in this slide, still data fusion is possible, but it's something that in a very nice review that was actually written in the context of metabolomics, not of food quality, was defined conceptual fusion. It means that, for instance, I am not analyzing the very same set of samples with the 3 instrumental platform, but I am analyzing samples that I can consider to be related. Maybe I couldn't analyze exactly the same, but I was taking samples from the same origins in relatively close time for sampling. So they are not directly comparable because they are not exactly the same samples, but I can still, based on my chemical knowledge, incorporate the information that I get from the different sets of measurements. So there's still something that I can do. Of course, this is not what I was referring to or what I would refer to as a first option when I'm speaking about data fusion. So, but this is still a multi-block configuration where I can incorporate information from the different blocks. This is the case that we will be discussing a bit more. So the case where the sample mode is in common. And in this case, I am using the different instrumental platform or the different sensors to characterize the same set of samples. Here, this is something that I will not be speaking, but I showed you a possible example, so the case of batch processing where the samples are different, but the variables are the same. And there can be the case, actually, where we have not both the samples and the variable modes in common. This is actually something that it could be analyzed using our multi-block tools, but actually gives rise to what is a different data organization, because I could, since these are exactly the same, I can put my matrices one after another to form a data cube. And I could think of analyzing this data with additional tools that are called multi-way, not multi-block, multi-way methods to exploit this double relation between the samples and the variable. So with something that is called trilinear methods. The PCA is called the bilinear methods because in mathematical terms, the model is linear in the sample direction and linear in the variable direction. So the model is linear in the scores, and is linearly related to the X matrix through the scores and the loadings. They are both linearly related. If I add a third direction by juxtaposing all these matrices one after the other, I would have a data cube. That, of course, we will not have time to discuss. So you see it here, that's a data cube. And the thing is that as told, and this is something that I anticipated, let's say the simple case is where I have data that are all coupled along one direction or the other direction, or in some strange case along both directions. But nowadays, since the thing is that you see that scientific publication, let's say scientific research, they follow the need that emerge from our data. And since there are more and more the cases where data, multi-block data are produced, even the models are becoming more and more evolved. So nowadays it's not infrequent to find algorithms that are able to deal with this case where one matrix is coupled across the samples and the other matrix is coupled across the variables. Or this case, for instance, when I want to fuse for a data table with this kind of strange structure that we would call the data cube. I say strange structure, but this is something that you would encounter quite frequently with some of the most commonly used experimental techniques. If you think this configuration means that I am measuring for each sample a two-dimensional landscape, HPLC UV, HPLC MS, GCMS, excitation emission fluorescent, just to name a few techniques that give you such kind of data. And in this case, of course, I have tools for fusing data that have matrix and cube and even higher order, like, because you can think, I cannot draw it, that the same case can be complicated. GC, GCMS. I get a data cube for each sample if I am taking full scan GC, GCMS. Because for each sample, I have a signal that is a function of retention time 1, retention time 2, and M/Z ratio. And if I generalize it to multiple samples, I have a 4-dimensional data array. So the good news is that we have tools for analyzing and fusing this data with a simple NIR spectrum. So the direction in common would be once again the sample direction, and I am able to fuse this kind of data. Okay. So why we could be interested in fusing our data? Well, the thing is that, okay, first of all, because if we consider to have multiple blocks of data, normally we have more parsimonious model. It means model with less component. And model with less component, they are in general more stable, more robust, and less overfitted. So it means that they are able to produce more accurate prediction if I'm doing prediction, and they are more easily interpretable if I am doing unsupervised analysis. So this already is a ground level of why I should do fusing, I should fuse my data. But second thing is that in some cases, I get added value in a straightforward interpretation, where, for instance, my different blocks have a natural ordering. So, sorry, okay, I have to speak closer to my mouth, but I think I'm speaking loudly enough so that you can listen to me. So think about food case, food production. You have one matrix is the property of the raw materials of a series of products. Second matrix, for instance, it could be some process variable measured along the production process. Third matrix is the characterization of the end product. And then I can keep track of the fact that these are different stages of the process, and even I can keep track of the relation between the blocks. So I can keep track on how some raw material properties do translate into the evolution of the process and do translate finally into the characteristics of the final product. So we will see, I will just mention, because I cannot do a course in data fusion going into the algorithm in 30 minutes now. So, but the idea is that I can give you some ideas about that. There are data fusion models that are sequential. So actually in putting the blocks one after the other, I can exactly describe how from one I go to the other and I go to the other again. And of course, for instance, if I am interested in the prediction of one or more properties, I can have an idea of how relevant are the different blocks in contributing to the final prediction. So, with this, I will give you one last hint about this general discourse, and then I will just try to give you a brief, very telegraphic example of some of the tools, of the chemometric tools that we have for the purposes. So with this description that I gave you in mind, then how should you navigate, especially if you are new in the field? So how should you navigate among the plethora of data fusion models that you can find in the literature? So actually, there are two aspects that you can look at. Two aspects that have to deal about interpretation and model stability indirectly. I will try to give you some hint about how this aspect translate into the interpretability and stability of the model. And since, and this was the relevance of my premise, we will be mostly speaking about component models, so models that extract from the different block relevant information in the form of latent variables or of component, in what aspect of the latent variables or what aspect of the original data is captured by the latent variable. That means how I am extracting information from the different data matrices. Am I capturing only the information that is common between, so that is systematically repeated or preserved across the different blocks? Am I taking into account also some information that is present only in a part of the blocks of the data, for instance, NIR and MIR, but not common to the other? Or am I also including that information that is relevant for describing my data, but is peculiar, for instance, only of the electrochemical sensors and is not copied in the other blocks? So, in my opinion, especially if you want to think about how to use your model, these are the two things that are important to stress. So the two things that you have to understand and look when you are approaching to data fusion protocol. Okay, this I can skip, otherwise I will speak other 2 hours. So let's understand first, the first, let's say, your first paradigm to try to understand where to orient when looking at a data fusion model. That means the hierarchy that is based on the level at which fusion occurs. So you have to understand that this is also, from an historical perspective, was the first and very basic classification of the data fusion model. I have to tell you that now, also following what I was telling like a minute before, since the complexity of the multi-block model that are arising is increasing, the good thing is that the new models that are emerging, they are usually combining what we will see and call the low-level and mid-level data fusion, because low-level and mid-level data fusion that I will be describing in a second, they have advantages and disadvantages, but they are normally the two approaches that are historically followed more frequently. And since they have drawbacks and pros and cons, actually the newly designed data fusion model, they are designed so to take the best from the two worlds. And they do it in a way, they do it because they actually will exploit the concept of hierarchically or successive or sequential modeling, as we will be seeing in a second. So data fusion means, of course, fusing the information from the multiple sources. So if you want to have a first idea of should I go in this direction or in this other direction, the first thing that you can look at is the level at which fusion occurs. So you will find often in the multi-block or data fusion literature reference to what is called low-level, high-level, and mid-level data, mid-level and high-level data fusion. So this is depending or focused on the level at the pipeline of data modeling at which fusion occurs. Low-level data fusion is the simplest that you can think of. It means taking each of my matrices, let's do, for instance, MIR and NIR data, do the proper pre-processing, so if I have to do like derivative or baseline correction, I, of course, put myself in the conditions that my data are as clean as possible for the successive stage, and then I am just concatenating the data. So if I was having like 50 samples measured with IR and NIR, let's say 2,000 and 3,000 variable, what I am doing, I am creating a longer data matrix just by juxtaposing the two matrices or three matrices or four matrices that I'm fusing. So what I end up with is a matrix that is the same number of samples and the sum of the number of the variables. So it's just wider. And then I am doing what I want to do, PCA, PLS, all the models that we described before. And we will repeat this if we have time in discussing the model. If I am doing this with PCA, I obtain a method that is called sum PCA, that just means PCA, normal PCA, operated on a long, wider data matrix that results from the concatenation of all the different matrices. If I am doing PLS, with a very low effort in terms of fantasy, I obtain what is called multi-block PLS. That's just PLS made on a wider data matrix. Of course, there would be some more to be told about that, but for you, the only thing that you have to understand at this very initial level is that, of course, since we discussed a bit before the break, all these methods, when they extract components based on explaining variance or covariance. So if I want to be fair, and this is actually the main drawback of these models, of the low-level data fusion models, all of them, is that if I have to be fair, I have to find a way to put, before calculating any model, PCA or PLS, to put the different blocks at the same level. So the most difficult part of this modeling is to find the suitable scaling that puts all the different blocks on an equal level before concatenating the matrices. Because this is absolutely needed. If I am failing in this, it can happen that my model is driven by the MIR, but not because the MIR is more relevant. I say MIR, it could be whatever, but not because it is more relevant in describing my data, but more because this was explaining by itself a higher variability. But this doesn't mean that it's relevant, because the two variability in the signal, they are different signal, they are not comparable, they are just different numbers. Or for instance, if I am taking raw data in MIR and first derivative in the NIR, the first derivative numerically has an intensity that is like 1,000 times less due to the Savinsky-Golay calculation. So just by this, I would, if I don't take any action, I would force my data or my explained variance in PCA to be driven by the first block. So what are the advantages on the other hand? Since I am concatenating experimental data, then when I am looking at the model parameter, loadings, regression coefficient, and so on, they are directly interpretable because they are directly expressed and in terms of the original variable. So I have a model that can be easily interpreted in terms of the original variable. There is an additional drawback. There is an additional drawback about that, and the additional drawback about that is that since I am concatenating experimental data, I am increasing the information, but I am also extremely increasing the unuseful information, so the spurious variability. So normally, low-level data fusion doesn't perform as well as the other data fusion protocols. Based on this consideration, I am doing the other opportunities mid-level data fusion. In mid-level data fusion, the idea is that I am partly screening my blocks separately. And from the different blocks, I am taking only the relevant information. This relevant information is in the form of features. These features are either latent variables. So for instance, I'm doing PCA on the two matrices, and I am just then eventually fusing the scores. I am not fusing the original data, but I am fusing features, latent variable, but I can also do variable selection. So I can just grab not all the data, but selected columns of my original data, and I am concatenating those columns. So what I am normally doing it with components. So it's more often that I am doing by fusing components. So what's the advantage? The model is cleaner, it's more stable. I still have to do some sort of variance equalization, so some sort of scaling, but it's more straightforward than in the previous case. the model is highly parsimonious and more stable. I am keeping noise apart from my fused data. What's the disadvantage? When I am looking at the data fusion coefficients, so at the loadings or the scores of the fused data, especially the loadings, they are in terms of the features that I have extracted. They are not in terms of the original data. So interpretation is less straightforward than in the previous case. I have to go back, for instance, to the loadings of my individual model to understand the contribution of the experimental variables, and then I have to mix this with the loadings of the data fused model to try to get an interpretation. In high level is mostly operated with predictive modeling, because high level means fusing the outcomes of the model. That means, in general, fusing the predictions. So I want to understand whether my unknown wine samples comes from the Douro region, for instance, and I build like individual classification models, one with the IR, one with the NIR, one with the UVVs, one with the electronic nose, one with the electronic tongue, and so on. And then I see, first model tells, yes, it comes from the Douro region. The second one says no. The third one says yes. The fourth one says yes. The fifth one says no. And then what I can do, I am fusing the outcomes. In the easiest way, it could be majority voting. 3 versus 2, the sample comes from here. Otherwise, I can do more complicated, like Bayesian fusion, in order to have a more elaborated operation. But this is the idea. So that's why it's normally done in terms of the predictive models. So my time is almost done, even if we started a bit later. So what I wanted to show you, I already spoken about the generalization of PCA and PLS. So this is just a further example to tell you graphically how would we normally do low-level fusion. You can think about the same already with PCA. With PCA, you just don't have the Y. But the idea is that low-level fusion that is called some PCA or simultaneous component analysis, they have slightly synonyms in the case of PCA, and it is called multi-block PLS in the case of PLS. I have the different data matrices. This could be ETONG, this could be ENOS, and this could be IR, for instance. I need to make them comparable. It means that I have to find the suitable scaling before concatenating. I concatenate the matrices, and then I calculate PCA, or if I have a Y, PLS or PLSDA. So that would be the easiest way of operating. And this would fall in the domain of low-level fusion. Then, just to give you a taste, it would be a very brief taste because time is over, of what we can do more, I will just cite these techniques. So I told you that nowadays, it means in the last 5 to 10 years, the number of cases with data fusion is needed, and you see, because I mean, you have felt this urgency as well, is increasing. And so, of course, by having much more cases and much more complicated cases, of course, like the attention of theoretical chemometrician is also moving in developing tools that are as effective as possible to deal with such kind of data. So this is a proper example. It was actually developed in its first application in Nofima. Nofima is a research institute in Norway that is based on fishery and food. So the idea and let's say the starting point was given by real problems that were involving multiple data matrices. This is called sequential and orthogonalized PLS, or SOPLS. Why I decided to show this model? because it goes in the direction of being a sequential model. So for instance, if you have a natural ordering of your blocks, raw material, process, end product, and so on, it keeps track of the order of the blocks because the information of the block is incorporated sequentially. Of course, it works also when there is no logical or natural ordering of the blocks, but when you have it, it gives you an added value. Then the good thing is that since it is sequential and it has also that orthogonalization step in the middle, it couples the advantages of the low level, so all the model parameters and all the interpretation is in terms of the originally measured variables, but then eventually, so at the end, the fusion occurs at the level of the scores. So it's a mid-level fusion in practice, but by the way the modeling is operated, it keeps tracks of the different steps, so model parameters are explicitly or can be calculated directly in terms of the original variables. So it gives you a straightforward interpretation. The idea, that's why it's sequential and orthogonalized. This you see the pipeline. Of course, I will not go very much into the mathematics, but I want to tell you qualitatively what the algorithm does. First, it calculates a PLS regression if we want to make calibration between the first block and the Y. And it does it extracting a certain number of components, and you get a predicted Y. But then it may be not enough. So the information in the first block, let's say in the mid-IR, could be not enough to give you a perfect calibration of the property that you want to calibrate. Then what you do, you remove the information that you have already fitted through this orthogonalization step, both from the Y and from the X. From the Y, it means that the second fit is done on the residuals. From the X, it's a bit tricky, but it does it through a process called orthogonalization. The idea is that you remove from the second block, so for instance from the NIR, the information that is correlated to the information of the previous regression. And then I calculate a second PLS model and a third and so on. And eventually I can express all of this into a global model, and this global model actually can be expressed as well through regression coefficients that are defined in terms of the original variables. So what is important here? I mean, because of course, it's an overload of information. So let's try to stick to the relevant part. So what is the relevant point of this model? First of all, it's a sequential model. It means that at each step I can evaluate through some tools whether the addition of the second block pays me off or not. So I can check, for instance, is really needed that I introduce also the NIR once I have measured the MIR for my calibration? Is it adding something to my model or not? So this is important because, of course, it's interesting to fuse data, but it's also interesting to know when adding further information is just copying something that I already knew. So, of course, since measurements are nice but are also costly, it can be useful for me to understand whether it's really worth to measure a second set of sensor outcomes or not. First thing. Second thing, I can, especially when there is no logical sequence in my blocks, by playing in the order of the blocks, so by making one model in which NIR is first and MIR is second, or vice versa, I can have an information of which components are common, so which part of the information is common across all the blocks and which part is unique. So that other parameter that I was telling you. Of course, this is something that for the moment you have to trust me about, because I will have to show you mathematically how to do it. But you can think that if you play safely, and this was also reported in some of the paper, in exchanging the order of the blocks, very often there will not be any difference in the quality of the prediction. So prediction will have more or less the same root mean square error or the same R square. But I get a nice insight about which part of information is shared by the different block and which part of the information is relevant but proper of a single block. So like this component is unique for the NIR. So it's a part of information that I need and that stays only in this block of data. So you see that, of course, by getting more and more into this kind of domain, you can play with more information and you can choose, for instance, the kind of model that can be more suitable for you. Recently, like a couple of years ago, with some colleagues, we published a review about the application of data fusion to food-related problems. So I can share this with you if you are interested in having an overview of some of the possible application of these models, even the most recently devised one. So I think I should stop here. I hope that I gave you an overview. As I told you, I mean, I was focusing more on giving you a sort of roadmap, because rather than telling you this, and this, because probably 1 minute after, these names would have been forgotten by you. So I hope that this was giving you at least some orientation in what to look for and what you can do and what to look for in a data fusion model. Of course, I'm very happy to answer your question, not only now, but even if you would have it in the future, and give you advices if you would need it. Thank you.
Yeah, so if there are any questions for this part of the presentation. I think, yes, Federico said we can contact him, whatever we need. Probably there is really a lot after this, so he gave us a flavor, yeah.
So Federico, just a quick question is about what do you think is, like for the beginners, the essential tools that should play with for being introduced to this topic? So just a kind of, not a really question, more a matter of advice, just what is the starting point that you recommend for the newcomers?
Okay. That's a difficult question. Because for instance, like, the thing is that it depends on the kind of information that you want in the end. Because, of course, the simplest one would be to use like multi-block PCA and multi-block, so some PCA and multi-block PLS, because they are the simplest. So this is something that you almost don't need a dedicated software to do it. So provided that you are fair with the pre-processing, because it should be proper between training and testing. But I mean, in general, you don't need a dedicated software to do it. And they are the tools that are matching naturally something that one is used to deal with. But of course, they are also the more basic, and there are many fishes in the sea and many things that are more appropriate. I mean, personally, I like very much this method because I find it very versatile.
It seems very rational.
Yeah.
So that's what I just picked. It seems that you follow, like, you
can find a rationale in the way that you are adding the blocks.
And of course, for instance, I didn't have time to show it in detail, but the concept nowadays, that especially in the exploratory data analysis, like to understand like which information is shared between the blocks and which is unique. I think it's something that has been emerging more and more. And in this context, for instance, there are some nice and even, I would say, simple to understand tools also for exploratory data analysis. One of these that is a PCA, GCA, so the application, the coupling of principal component analysis and generalized canonical correlation analysis. That's a relatively simple way of understanding which part is shared between the different blocks and which part is unique.
All right. So yeah, thank you very much again, Federico, for